Time travel is a staple of science fiction, and it's been conceived of in many different ways. Given that science fiction has inspired so many real technological advances, everything from cell phones to submarines to nuclear power, one can legitimately wonder whether the ability to time travel might actually be in humanity's future. And it might, if time travel is actually possible. To discover whether it is, as we enter the realm of metaphysics, the study of the nature of reality, which, among other things, aims to answer philosophical questions raised by science, let's look at a variety of ways that time travel has been portrayed in science fiction. In one of my favorite shows from when I was young, Quantum Leap, Dr. Samuel Beckett is able to travel in time, but only into the years of his own past. He trades places with past persons like Lee Harvey Oswald, but is seen by others as that person. Once he has set right what once went wrong, for example, according to the show, Sam was the Secret Service agent who saved Jackie Kennedy, he leaps into another body. Although the show did not explain much about why he leapt into the bodies he did, there were some hand-waving explanations to explain how. As the title suggests, it has something to do with quantum mechanics. Now, I don't think it has anything to do with actual quantum leaping. That's when an electron moves from one orbit of an atom to another without passing in between. It just appears. And that's cool, but that's not going to get you time travel. But there are elements of quantum mechanics that might. Take quantum entanglement, for example. If two particles are entangled, their properties must always match, or in the case of spin, must be exactly opposite. If one is a wave, the other one must be a wave. If one particle becomes spin up, its entangled particle must become spin down. And this happens even if one particle takes on a property, while the other is light years away. It's as if they can send instantaneous signals to each other. Now, people can't actually send information via these signals because although you can make particles take on properties by measuring them, you can't control what properties they take. For example, if you force an electron to take on a spin by making it pass through a detector, you can't dictate whether it takes on an up or down spin as a result. According to quantum mechanics, a particle's spin is assigned at random. But if we suppose that aspect of quantum mechanics is wrong and you could control it, well, then you could control the properties of the paired particle too, even though it's light years away. If you wanted to have spin up, you just make the particle near you have a property of spin down. So to communicate with, say, your mother across light years, you need to simply do the following. One, work out a system of communication. You could, for example, use Morse code and use up for dot and down for dash. Two, arrange for a stream of particles near you to be entangled with a stream of particles near your mother. And then three, make the particles near you take on the up or down properties necessary to send your message. Now, that's a lot of ifs, but science fiction is built on ifs. And if we grant them, and we squint just a little bit, we might be able to see how the time travel in Quantum Leap could work. Because a few years after Quantum Leap went off the air, something called a quantum eraser showed that entanglement not only holds across long distances, but also backwards in time. The quantum eraser was first tested by Yoon Ho Kim. I'm simplifying a bit here, but roughly speaking, in a quantum eraser, two entangled photons are sent through a device. Photon A to a detector, and then photon B through a series of two-way mirrors. Now, photons are waves, but can collapse down into particles. In the eraser, if the B particle randomly takes a certain path, it becomes a particle at the end of its journey. If it randomly takes another path, then it stays a wave. if you do this over and over, and you take all the A photons that were entangled with the photons that stayed waves, you'll see that those A photons hit their detector as a wave. They create an interference pattern. And the A photons paired with the photons that became particles don't. They hit their detector as a particle. And that's what should happen. Quantum mechanics demands that paired particles must always have the same properties. The kicker is this: each A photon hits its detector long before its B partner finishes its journey. Even before the B particle reaches its first two-way mirror, the A particle has already hit its detector. It's as if the A particles know what path their partner will take and how they will end up before they get there. Or, at least on some interpretations of quantum mechanics, as if once the B particle finishes its journey, it sends a signal back in time to let its partner know whether it should be a wave or a particle. So, if Dr. Sam Beckett has developed a way to dictate what properties quantum particles take on, and then quantum entangles the particles of his brain with the brain of someone in the past, then he could potentially control their actions. Perhaps that's why he can only travel to a past state within his own lifetime. There must be an earlier version of his brain nearby at that past time to facilitate the entanglement. That something like this is going on is suggested by the fact that Sam's trusty companion, Al, appears to Sam as a hologram that only he can see and hear. Al's transmitting himself into the visual and auditory centers of the brain that Sam controls. Now, that explanation's not entirely scientifically sound, and the last episode might negate it, but I think it's fun. In Star Trek, time travel happens in many different ways. My favorite is the slingshot maneuver in Star Trek IV, The Voyage Home, where Mr. Spock uses the sun's gravity to accelerate their ship and then whip around the sun, appearing on the other side in the past. The idea that this could facilitate time travel is loosely based in Einstein's relativity. As I explained in Exploring Metaphysics, relativity entails that space-time, the fabric of the universe, is actually a substance that is affected by the mass and rotation of large objects. According to Austrian physicists Josef Lenza and Hans Thierink, if an object is massive enough and rotates enough, it collects space-time around it, kind of like putting a rotating cylinder in a bucket of water would cause a whirlpool. According to Willem Jacob von Stockholm and Frank Tipler, if you had a spacecraft going near the speed of light and allowed your spaceship to be pulled in by the rotation and then orbited a certain amount of time, if you then exited the orbit at a certain angle, you would find yourself at a moment in time before you began. The problem with the scientific accuracy of the Star Trek stories is that the sun simply doesn't have enough mass to produce the required effect. Indeed, the only thing massive enough is a giant rotating cylinder of infinite length. Needless to say, if Spock thinks such an object is even possible, he's out of his Vulcan mind. So it doesn't seem that this makes time travel possible. A kind of time travel that could actually happen, however, is depicted in the original Planet of the Apes. It has its astronauts travel to the future by essentially traveling away from the Earth and back again at very high speeds. While they traveled in their spacecraft, only a few years passed, but then the Earth aged so much that once they returned, it was unrecognizable. Oh yeah, spoiler alert, that's the big reveal when Charlton Heston sees the Statue of Liberty at the end of the film. Oh my God, he was wrong. It was Earth all along. Traveling away and then returning to the Earth at high speeds would have this effect because, according to the theory of relativity, time passes more slowly in reference frames that are traveling faster than you. Now, it's difficult to fully explain how this works. If you're interested, David explains it very well in his book, The New Time Travelers, A Journey to the Frontiers of Physics. The basic idea is that because on such a trip you are in 3 reference frames, one inertial as you travel away, one non-inertial as you turn around, and then another inertial as you travel back, when you return, you will find that more time has passed for the inhabitants of Earth than has passed for you. The problem is the effect of such time dilation is just not that pronounced. A 62-year round trip at near the speed of light would only gain you 10 years. 72 years would have passed on Earth. Needless to say, unless Charlton Heston can survive hundreds of years of hibernation, he's going to be long dead before he's able to complete a lengthy enough journey to enable Earth to become the planet of the apes, especially given his tendency to smoke cigars in spaceships. But at least this one is possible. But my personal favorite time travel series is Doctor Who, which expounds on the adventures of the Doctor, a Time Lord from Gallifrey who travels through time and space in his TARDIS, which stands for Time and Relative Dimension in Space. Although more than 50 years of Doctor Who canon is hard to keep track of, and there are many ways that time travel happens in the show, I've always understood the TARDIS to travel in time by traversing what is called the time vortex. It's that funky tunnel you travel through during the title sequence of every episode. Interestingly, time travel via what we might call a time vortex could theoretically be possible. Here's how. A wormhole is like a portal between 2 places. It's created when 2 distant points in space are joined by space-time itself being bent in a higher dimension. This is often explained by drawing 2 points on a piece of paper and then folding the paper to connect those 2 dots. By passing through the wormhole, you can travel long distances instantaneously. So, say you have a wormhole, but its 2 ends are fairly close together. Suppose you were to take whatever is keeping one wormhole open and put it in a spaceship, and then make it and its wormhole travel away at near the speed of light, and then return again. Just like in Planet of the Apes, upon your return, one end of the wormhole would be older than the other. Side A may be 60 years old, while side B is, say, 70. You'd have a time-dilated wormhole. If you were to step into side B of your time-dilated wormhole while it is 70 years old, you would emerge from side A when it is 70 years old. But that side won't be 70 until 10 years after the moment you stepped into side B. So you will have traveled 10 years into the future. But of course, in 10 years, side B will be 80 years old. So you could just step into it and travel 10 more years in the future. And you can just repeat this process ad infinitum and travel into the future or back into the past as much as you wanted. As long as the wormhole stays open and you don't want to travel to a time before its creation, you could travel where you wanted. To facilitate their ability to travel in time, the Time Lords of Gallifrey could create an infinite series of such wormholes, spanning all of time and space, what you might call a time vortex, and then build machines called TARDISes that are able to navigate this vortex. Now, is this really possible? Well, to do so, the Time Lords would not even have to create wormholes. Wormholes actually happen all the time. There's probably one happening near you right now. So that's good for the possibility of time travel. Unfortunately, these wormholes are super tiny, smaller than even quantum particles, and they blink in and out of existence so quickly that not even light can travel through them. That's bad. Of course, We could enlarge them and keep them open. And if we could build a time machine. That's good. Unfortunately, according to physicist Kip Thorne, this would require the use of something called negative energy to circumvent the average weak energy condition. And negative energy is not known to be real. That's bad.
Can I go now?
Interestingly, Benjamin Tippett and David Sang have written a paper on whether time travel via TARDISes is actually possible. It's appropriately entitled Traversable Achronal Retrograde Domains in Spacetime, TARDIS. It's a bit too complicated to explain here, but their conclusion is encouraging. It seems that such a device is physically possible in our universe. Closed time-like curves, which wormholes can create, are possible in our universe, and they could theoretically allow one to travel in time. Of course, they observe limitations which may prevent us from ever constructing a TARDIS, but then again, the universe is so large and old, maybe eventually someone will overcome those limits. If you are interested, they wrote a version of the paper for laymen called the Blue Box White Paper. I encourage you to check it out. But the movie with the most scientifically accurate depiction of time travel is the movie I ask you to watch for this lecture, Christopher Nolan's Interstellar. It's set in a future where Earth has been decimated by ecological disaster. The protagonist, Joseph Cooper, a former NASA pilot, lives on a farm with his beloved daughter Murphy, or as he calls her, Murph. After a dust storm, they notice a strange pattern of dust on Murph's bedroom floor. Murph thinks she has a ghost in her room, but Cooper realizes the pattern is due to gravitational variations emanating from Murph's bookshelf. Decoding the pattern leads them to a secret NASA installation, where they learn of NASA's secret plan to try to save the human species. See, a wormhole that leads to a distant planetary system has appeared near Saturn. And years ago, NASA sent 12 brave astronauts through that wormhole to try to find a planet suitable for human life. 3 of them, Miller, Mann, and Edmonds, have sent signals back through the wormhole that seem promising. The NASA scientists asked Cooper to pilot the spaceship Endurance on a mission that will determine which planet is most habitable and then transplant 5,000 human embryos to that planet to restart the human race. It's when Cooper and his team explore the first planet, Miller's planet, that we get perhaps the most scientifically accurate depiction of time travel in all of science fiction. But to fully understand it, we need to understand a bit about black holes and the effects of gravity on time. So let's set Interstellar aside for one moment. First, black holes. Black holes are collapsed stars that are so dense and massive that not even light can escape their gravitational effect. Now, because of this, they can't be observed directly. But they are surrounded by what's called an accretion disk, a ring of particles that surround it like the rings of Saturn. And the accretion disk emits X-rays that can be detected. The black hole nearest Earth is V616 Mon, and Sagittarius A star is the name of the supermassive black hole that sits at the center of our galaxy. It's about 4 million times the mass of our sun. Black holes are so massive, in fact, that the effect of their gravitational forces increases exponentially as you approach them. This means that the gravitational pull on 2 objects near a black hole can be drastically different, even if one is just a meter closer than the other. For example, if you were to approach a black hole feet first, the gravitational pull on your feet would be so much stronger than the pull on your head that you would essentially be stretched out into the shape of a piece of spaghetti. Physicists actually call this spaghettification. Second, the effects of gravity on time. Because of the aforementioned effect of gravity on space-time, the more massive an object is, the more space-time collects around it. This means that the closer you get to a massive object, the slower time will pass for you. This is a bit simplistic, but you might think of space-time like maple syrup. The more space-time a massive object pulls in, the thicker it gets, and so the slower you move through it. Although, from your perspective, you wouldn't notice the difference like you would if you were stuck in syrup. This effect increases exponentially as you approach the black hole as well. The closer you get, the slower time moves, and drastically so. A stellar example of this effect is in the 10th series episode of Doctor Who entitled World Enough and Time. The Doctor and company come across a colony spaceship 400 miles long, trying to reverse away from the gravitational forces of a black hole. The ship was empty, save for a maintenance crew of 50 at the top. But 2 days after 20 crew members went to the lowest decks of the ship to reverse the rear thrusters, the ship is teeming with thousands of life forms. What happened? Because the bottom of the ship was 400 miles further away from the black hole than the top, those 20 crew members who went to the bottom found that time passed much more quickly. While only a few moments passed at the top, those at the bottom experienced 10 years. They got trapped and went on to live their lives. And they had children and grandchildren and spawned countless new generations filling up the ship. All the while, only 2 days passed at the top. And this brings us back to Interstellar, because Miller's planet is orbiting a supermassive black hole called Gargantua. And Gargantua is about 100 million times the mass of our sun. Indeed, it warps space-time so magnificently that you can see its entire accretion disk all at once. That magnificent light that surrounds the top and bottom of the event horizon is actually the backside of the disk. The unique way Gargantua appears in the film was derived by equations that physicist Kip Thorne generated to describe it. Indeed, Christopher Nolan hired Kip Thorne to make sure the film was as scientifically accurate as possible. And something else Kip Thorne figured out is that given how close Miller's planet is to Gargantua, the time dilation that it would be subject to would be massive. For every hour you spend on Miller's planet, 7 years will pass on Earth. That's how thick space-time is around Gargantua. Cooper and his team go down to Miller's planet in a shuttle, leaving behind the Endurance. They find the wreckage of Miller's ship in a large ocean of water, but the wreckage is still all together. This confuses them at first. After all, Miller landed on the planet years ago. But then they realize that from the planet's perspective, Miller landed just hours ago. If Miller landed 21 Earth years ago, she would have landed on this planet only 3 hours ago. Then they realize another problem. An object that close to a black hole is subject to enormous tidal forces. And since they're on an ocean, this means giant tidal waves. They had intended to only stay a few minutes, long enough to collect Miller's data and run. But when a tidal wave nearly destroys them and floods their engine, they are stranded for much longer. And by the time they get back to the Endurance, 23 years have passed on Earth and on the Endurance. Cooper sits down to watch a series of messages from his family that have been building up while he was gone. And he discovers that his daughter is now older than him and working for NASA. In effect, he has traveled in time. What's so great about this is that this actually is what relativity entails would happen if you visited a planet that close to a massive enough black hole, one that's massive as Gargantua. It's all based on actual equations. So again, time travel is indeed possible. Of course, one might argue that this doesn't really count as time travel. Cooper is just experiencing change more slowly. But That actually does count, according to David Lewis's widely accepted definition of time travel. An object time travels if and only if the difference between its departure and arrival times, as measured in the surrounding world, does not equal the duration of the journey undergone by the object. Now, given what we have discussed, the kind of time travel that seems most possible is time travel to the future. But what about time travel back to the past? Well, Interstellar can help us explore that too. After the failure at Miller's planet, Cooper and his team try to explore man's planet. But it turns out that man is selfish, horrible, and destructive. After man almost successfully sabotages their mission, Cooper and the only surviving member of his crew, Dr. Amelia Brand, realize that their last hope is to try to reach Edmund's planet. They don't have enough fuel, but they can use Gargantuan's gravitational force to propel themselves there, but only if Cooper ejects himself. He does, and is pulled into the black hole. Now, in reality, he'd likely just be killed, stretched into spaghetti. But we really don't know what lies beyond the event horizon of a black hole, the point at which its gravitational pull is so great that not even light can escape. So Nolan chose Cooper's journey beyond the event horizon of Gargantua as an opportunity to take some artistic license. What Cooper finds beyond the event horizon is a tesseract, a three-dimensional representation of a four-dimensional object. In this case, it's his daughter Murph's bedroom at every moment of its existence, which he can view from behind her bookshelf. He slowly realizes that he can send her signals back through time, and thus he was the ghost in her bedroom all along. Remember how they observed those strange patterns of dust on the floor that led them to the NASA installation in the first place? It turns out that was Cooper himself sending messages from the future from inside Gargantua. But this raises a philosophical puzzle, a seeming paradox. Cooper went on the mission only because he sent Murph signals explaining how to get to the installation. But he was able to send Murph signals explaining how to get to the installation only because he went on the mission. So what caused what here? If you can't have A without B, but you can't have B without A, how do you have either? We have what philosophers call a causal loop. And it's not the only one in Interstellar. We later learn that it was a race of five-dimensional beings that placed the wormhole near Saturn, and that placed the tesseract inside the black hole. They wanted Cooper to be able to communicate with Murph so he could send her the information. So the five-dimensional beings are saving the human race. But it turns out the five-dimensional beings are the human race, or what the human race will eventually become long after it has been saved. So humanity still exists only because it saved itself, but it saved itself only because it still exists. It's another causal loop. In fact, causal loops appear constantly in time travel science fiction. Perhaps the most famous causal loop appears in one of the most famous films ever, Robert Zemeckis' Back to the Future. In Back to the Future, Marty McFly travels from 1985 back in time to 1955 in Doc Brown's DeLorean. Marty then has to enlist the help of the 1955 version of Doc Brown to get back to 1985, Back to the Future. While in the past, Marty ends up having to play guitar at his parents' prom, the Enchantment Under the Sea dance. As a final encore, Marty rocks out to Johnny Be Good. And while he's playing it, Marvin Berry calls his cousin Chuck and lets him hear it. And of course, Chuck Berry eventually records the song. So Marty knows Johnny Be Good only because Chuck recorded it, but Chuck recorded it only because he heard Marty play it. So we not only have a causal loop, Johnny Be Good seems to be what's called a Jenny, a self-created object or piece of information, an object or information that has no causal beginning. Interestingly, time travel stories often involve the time travel machine itself being a genie. Someone uses a time machine to go back in time and teach himself how to build a time machine. Indeed, depending on how you interpret the movies, you might think this is how the DeLorean time machine is invented in Back to the Future. In the third movie, the 1985 version of Doc Brown buries the time machine in the distant past for his 1955 self to find, complete with instructions on how to repair the time circuits. But one is left to wonder, would the 1955 Doc Brown ever have figured out how to build a time machine if he had not already read the instructions? Sure, before that happened, the 1955 Doc Brown drew a picture of the flux capacitor, what makes time travel possible, but maybe he didn't know how to make it work until he read those repair instructions. But all this isn't just fun to consider. It can actually tell us something about the possibility of time travel. How? Things like causal loops seem to be logically impossible. That's why they're called paradoxes. But that which is logically impossible not only isn't true, it can't be true. As philosophers would say, there is no possible world in which a genie exists. But if time travel to the past is possible, a genie could exist. Therefore, it must be that time travel to the past is logically impossible. It doesn't occur in any possible world. Other paradoxes created by the possibility of time travel to the past also suggest this. Consider again the plot of Back to the Future, in which Marty nearly annihilates his own existence by traveling to the past and keeping his parents from falling in love. The movie suggests that this makes Marty and his siblings slowly fade out of existence. But of course, this is nonsense. Either he will be born or he won't. But if he's not born, then he won't travel back in time to prevent his parents from falling in love, which means they will fall in love and he will be born, which means he will travel back in time and prevent them from falling in love, which means he won't be born. You get the idea. He will, if and only if he won't. The ability to travel back in time would give time travelers the ability to prevent their own existence. And that's logically impossible. It's called the grandfather paradox, and it's supposed to show that travel backwards in time is impossible. If it were possible, then it'd be possible to kill your own grandfather at a time prior to his siring of your own father, and thus negate your own existence. Since that logically can't happen, neither can time travel to the past. But would time travel into the past really allow one to annihilate oneself? Are causal loops really logically impossible? Are these truly paradoxes? Or are there ways out of these problems? It is to those questions that I want to turn in the next lecture. But before we address them, there are a couple of things I want you to do. First, watch the Doctor Who episode called Blink. It's the first episode that most Whovians suggest that you should watch if you have never seen Doctor Who before. It's the perfect introduction into the Doctor. As you watch, ask yourself, who started the DVD commentary conversation between the Doctor and Sally Sparrow? Then, if you can find it, I want you to watch an episode of the TV show Futurama called Roswell That Ends Well. Afterward, ask yourself, does the episode solve the paradox or merely avoid it? And what's the difference between those two things? Okay, I'm going to time travel to the beginning of the next lecture. See you then. In the episode of Doctor Who I asked you to watch for this lecture, one called Parallels, Season 7, Episode 11. What? No, I asked him to watch Blink. parallels is that episode of Next Generation where all those versions of Lieutenant Worf, Worves. The plural of Worf is Worves. Sorry about that. I have no idea where that video came from. Anyway, what I asked you to watch was Blink, a Doctor Who episode from 2007. In it, Sally Sparrow discovers an alien race called the Weeping Angels. The angels freeze into stone when they're being observed, but can kill you when they're not by sending you back in time and feeding off the potential energy of the future days you would have lived, essentially letting you live to death. This is how they've trapped the Doctor, a Time Lord, in 1969 without his time machine, the TARDIS, which is stuck in 2007. To get it back, he arranges for Billy Shipton to plant Easter eggs, secret video clips, on 17 different DVDs, the 17 that Sally Sparrow owns. These Easter eggs show the Doctor carrying on half a conversation. Where's the other half? In 2007, carried on by Sally Sparrow. The Doctor's able to maintain his half of the conversation because he has a transcript of what she will say 38 years before she'll say it. How? Well, when Sally finally watches the Easter egg, she figures out that the Doctor is talking to her and carries on her half of the conversation. Sally's friend Larry then writes it down. Then, at the end of the episode, after Sally sends the TARDIS back to the Doctor in 1969, she runs into the Doctor at a moment in his life before he is trapped in 1969. She gives him the transcript so that one day in his future, when he needs it to create the Easter eggs, he will have it. The question to consider is this. Does Sally give the Doctor this transcript because she was saved by the Doctor, or was she saved by the Doctor because she gave him the transcript? The Doctor and Sally's conversation seems to have no causal origin. Take the Doctor's half of the conversation. Although Larry writes it down, he is only copying what the Doctor says. Yet the Doctor only says what he says because it's written down on the transcript. So, who is the author of the Doctor's words? It's not Larry. He's only copying the DVD. But it's not the Doctor. He's just reading off the transcript. As we discussed last lecture, a self-created object like this is called a Jenny. And Jen, that's the plural of Jenny, are all over this episode of Doctor Who. For example, at the beginning of the episode, Sally is with her friend Kathy Nightingale in an abandoned house. She leaves her behind when she hears the doorbell ring. Because Kathy is alone and unaware of the danger, the angels touch her and manage to send her into the past. Once there, Kathy meets a boy, has a family, and eventually a grandson, and it was the grandson who rang the doorbell. He had promised his grandmother, Kathy, that he would deliver a letter to Sally at this moment in time. Yet it was only because Sally was distracted by the grandson and him ringing the doorbell that the angels were able to get to Kathy. So does the grandson's visit cause Kathy to be sent into the past? Or does Kathy being trapped in the past cause the grandson's visit? As we've seen, the possibility of Jen seems to make time travel into the past impossible. After all, causes always precede their effects, right? So if A caused B, A came before B. But if B also caused A, then B came before A. But by the principle of transitivity, that means that B came before itself. And that's logically impossible. So time travel into the past is logically impossible. This argument, however, against time travel to the past, begs the question. Time travel essentially is the suggestion that causes sometimes come after their effects. If Marty travels from 1985 to 1955, his activation of his time machine in 1985 comes after, but is the cause of, him appearing in 1955. So if your argument against the possibility of time travel begins by assuming that it's impossible for effects to precede their causes, you're basically just assuming the truth of what you're trying to prove. So that argument won't work. The problem with Jin actually goes deeper. Regardless of what temporal direction the causal arrow points, it seems that causal explanations have to bottom out somewhere. Unless you arrive at a stopping point, you really haven't explained anything. But with Jin, there is no stopping point. A caused B, which caused A, which caused B, and on and on and on and on and on. This, it seems, leaves Jin without an explanation for their existence. They have no causal origin. And if there is no explanation for why they exist, then logically, they can't exist, right? Since time travel into the past would entail that they could exist, time travel into the past must be impossible. That's the argument. But that argument makes us wonder, are Jin really logically impossible? Is there really something incoherent about the concept itself? Not really. To explain why, let me slightly modify some of the doctor's words. People assume that time is a strict progression of moments, the past, the present, the future. But actually, from a nonlinear, non-subjective viewpoint, it's more like a block of wibbly-wobbly, timey-wimey stuff. That sentence kind of got away from me, but what does it mean? Well, our experience tells us that there is a fact about what moments are past, present, and future at any given moment. In the beginning, the Big Bang was the present moment and everything else was future. Later, the JFK assassination was in the present moment and everything else was either past or future. At another point, the sun exploding will be a present moment, etc. And if two events are simultaneous, that's because they were both present at the same time. But Einstein's relativity teaches us that this is not correct. Why? Because motion and consequently simultaneity are relative to a reference frame. Now, what does that mean? Think of two spaceships about to collide, say the Millennium Falcon and the Starship Enterprise. From the Falcon's perspective, or frame of reference, it's stationary and the Enterprise is moving towards it. But from the Enterprise's perspective, it's stationary and it's the Falcon that's moving. And from the perspective of someone, say, on Battlestar Galactica watching this whole thing, the Falcon and the Starship Enterprise are moving towards each other. What relativity teaches us is that no one of these perspectives is more correct than another. These are all equally accurate ways of describing what's happening. Just like you might say that your fork is to the right of your plate and someone across the table might say it's to the left, and you'd both be right. According to relativity, there is no fact of the matter about what's really moving and what's really stationary. It's all relative. What follows from this, once you realize that the speed of light is the same in all reference frames, is that there is also no fact of the matter regarding whether events are simultaneous. If they are simultaneous in one frame, they won't be in another. And neither description is right or fully captures what really happened. The classic thought experiment used to explain this involves two people, one inside a moving train and one outside it, and lights that turn on, one on the front of the train and then one on the back of the train, whose light beams meet in the middle of the train. From the perspective of the person inside the train, the lights turned on at the same time, meet in the middle. But from the other person's perspective, the backlight turned on first. Since the train is moving towards the front light and away from the backlight, that's the only way that their light beams would be able to meet in the middle of the train and the speed of light not change. Now, I know that was quick. I go into it in much more detail in exploring metaphysics. But the upshot is this. Because simultaneity is relative, for any given event A and any other event B that happens after it, there will always be some other event C such that C is simultaneous with A in one reference frame, but also simultaneous with B in another. But the only way that can be the case is if all these events exist together. And that's why relativity contradicts the common progressive view of time. Because the only way that can all be true is if all moments, what we would call past, present, and future, exist as a whole in a giant block, a block that has a bunch of different reference frames running through it, all dictating different things about which events are simultaneous with others in different frames, but none capturing the full truth. Kind of like a big block of wibbly-wobbly, timey-wimey stuff. Indeed, there is not even a fact of the matter about what moment in time is the present moment, and which moments are past and which ones are future. They all just exist. The JFK assassination is happening just as much as my utterance of these words is happening. They're all just moments in time. We seem to experience them in a progression, but as Einstein once said, people like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. Indeed, in the previously discussed movie Arrival, it seems that looking beyond this illusion is what learning the alien's language enables Dr. Banks to do. She can see the entire timeline, the block, as a whole. She no longer sees it in the inaccurate way that humans do, as a progression from past to future. But realizing that this is the true nature of time allows us to realize that there is nothing paradoxical at all about jinn. They seem paradoxical because they were running around in a circle. A caused B and B caused A. The causal explanation doesn't end anywhere. They have no causal origin. But if all of time is a giant block, which contains all moments in time, they do have a causal origin. The jinn came into existence along with everything else as the entire block came into existence. If we think of the universe as being created, it was not created as a batch of matter that grew and developed and became more complicated over time. It did not start with a single moment and then progress into a series of moments. All of space and time, the entire block, past, present, and future, came into existence as a whole, all at once, we might say, with its entire history intact. So, if that's the case, why couldn't it have a jinn within it? The explanation for them would be the existence of the block itself. Or you could think of it this way. When it comes to a jinni, nothing is unexplained. A explains B, and B explains A, and there's nothing else to explain. Now, you might think that the circle itself needs to be explained, but why think that if you don't demand an explanation for the line itself in the case of linear causation? In both cases, whatever accounts for the existence of the block suffices to explain either the jinni or the line. Richard Hanley defends the possibility of jinn in his fascinating article, No End in Sight, Causal Loops in Philosophy, Physics, and Fiction. He identifies many different kinds of causal loops, such as object loops and information loops, and he points out that some loops are easier to account for than others. Physical objects that exist in a loop will require some way to ensure that their matter is replenished. But at worst, Causal loops of any kind only require a grand coincidence. They are not logically incoherent. It's even possible to be one's own father or mother. What's more, since the actions of conscious agents can easily make grand coincidences occur, causal loops are much more likely in a universe like ours, one that has conscious agents in it. So, causal loops don't negate the possibility of time travel to the past. But what about the grandfather paradox, the other objection to time travel that we considered last lecture? It illustrates how time travel would make it possible to annihilate yourself before you traveled in time by, say, killing your grandfather before he sires your father. This would create a paradox where you annihilate yourself if and only if you don't. Since that is not even possibly true, the argument goes, time travel into the past cannot possibly occur. But many philosophers agree that this argument is not sound. In fact, there are two ways to avoid the conclusion of this argument. But before I explain them, it's important to point out that you can't answer the argument by avoiding the problem, like the characters in Futurama did. In the Futurama episode I asked you to watch, Roswell That Ends Well, the gang travels to the past and ends up causing the famous 1947 Roswell UFO incident. They are the ship that crashes. Professor Farnsworth warns Fry not to kill his own grandfather, Enos, but Fry's efforts to prevent this end up resulting in his grandfather's death. Fry places Enos a bit too near a nuclear test site. The writers avoid the paradox, however, by having Fry sleep with his own grandmother, thus making Fry his own grandfather. Essentially, instead of annihilating himself, Fry becomes a Jenny. This does not solve the grandfather paradox, however. It merely avoids invoking one. Why? Because the argument does not suggest that every instance of time travel would include a self-annihilation paradox. So telling a time travel story that avoids one doesn't answer the argument. What the argument does suggest is that time travel to the past seems to make possible something that is impossible: self-annihilation. To solve the paradox, one must explain why time travel could never allow for the possibility of self-annihilation. To do so, you basically have to reconceive the very nature of what time travel would do. And there are two ways to do this. The first is called branching time travel, a solution to the problem endorsed by philosophers Newell Belknap and David Deutsch. The suggestion is this: when you travel back in time, you do not travel to your own past. You travel to the past of an alternate universe, which has a past just like the universe you left up to the moment to which you traveled, but that also contains the event of you, the time traveler, appearing at that moment. You then proceed forward in time in that universe and deal with the consequences of your actions there. But you can't kill your own grandfather because your grandfather is in the past of the universe you left. You traveled to a different universe with a different grandfather. If you kill him, you will simply prevent that universe's version of you from being born. But the event of your birth is still safe and sound in your original universe. This conception of time travel can quite handily be used to make perfect sense of many time travel stories. Take the first season of the NBC show Heroes, for example, a show about heroes with special powers granted by their unusual DNA. It involved multiple episodes of time travel into the past by a time traveler named Hero. If you keep careful track, as Morgan Luck did in his chapter of my book, Heroes and Philosophy, you can demonstrate that the story is consistent. Every time Hero jumps back, he creates a new universe. Now, By the end of the first season, we are in our fourth universe, and Hiro is the only character that is actually from the original universe, but the story is at least logically consistent. Although it does solve the grandfather paradox, branching time travel cannot be used to make sense of every time travel story, even ones that explicitly try to explain their plot with the branching view. Take the second Back to the Future movie. Doc Brown and Marty travel from the peaceful town of Hill Valley in 1985 to Hill Valley 2015. While they're there, Biff steals the DeLorean to travel back to 1955 and give himself a sports almanac, and then returns the time machine to 2015. Doc and Marty then use it to return to Hill Valley in 1985, only to find that it is now a lawless dystopian wasteland. Doc explains this development by saying that Biff, giving his younger self the almanac, created an alternate timeline in which he gained wealth that enabled him to ruin the town. And that is the timeline in which they are now in. But that's not how branching time travel works. If 2015 Biff created an alternate universe when he stole the DeLorean to travel to 1955, then when he went back to the future, he should have arrived at the 2015 of that alternate universe, one where that universe's Biff is old and rich. He should not have returned to the future of the universe he left, where he got the DeLorean from Doc and Marty in the first place. But that's what happens in the movie. In reality, Marty and Doc would have been stranded in 2015 without a time machine. And if they built a new one and traveled back to 1985, they would have found it just like they left it, because it would have been an alternate universe just like the one they left up to 1985. To make sense of other stories, you have to tweak the branching time travel theory a bit. Take Donnie Darko, for example. It tells the story of a boy who was out for a walk one night when, out of nowhere, while he's communicating with a psychedelic rabbit, a jet plane engine lands on his bedroom. Somewhat thankful to be alive, he continues to live his life and then falls in love with a girl named Gretchen. But his meeting her, ultimately, although accidentally, leads to her death. When presented with the opportunity to go back and be in his bedroom when the engine falls on it, he takes it and dies, thus saving her life. Now, I'm not doing the movie justice, it's way trippier than that, but it seems to explain itself in terms of alternate universes. Indeed, the fictitious book featured in the film, The Philosophy of Time Travel, actually speaks in terms of tangent universes. And this, it seems, is what the psychedelic rabbit meant when he said the world was about to end. The universe in which Donnie lives will end, and a new one where Donnie dies will be created. But if we are to explain the plot in terms of branching time travel, there's one little hitch. If Donnie's traveling in time created a duplicate universe, just like the one he left right up to the moment before the engine fell on his room, well, that universe would also contain a duplicate Donnie out for a walk, who would go on to live his life. To make the story work, time travel must not only create a duplicate universe, but must also erase the duplicate of the time traveler from that duplicate universe at the moment of the time traveler's arrival. Now, that's fun, but although branching time travel can make sense of many time travel stories and solve the grandfather paradox, it still has two noteworthy consequences. First, it's not clear that it's really time travel. Although it would look like time travel to the time traveler, it's really just alternate universe creation. So to accomplish this, you would need to invent a machine capable of creating specific kinds of alternate universes, not a machine capable of traveling in time. This fact was demonstrated quite hilariously in the short film 1 Minute Time Machine that uses a slightly different version of branching time travel. It tells the story of a man trying to pick up a woman. When he makes a pickup mistake, he undoes it by traveling 1 minute back in time to try again. In the end, however, he learns that he's not traveling in time. His time machine actually just kills its user and creates a duplicate universe set 1 minute in the past, where another version of the user with memories of the original tries to pick up a different version of the same woman. And he does this 16 times. And towards the end of the film, we're treated to a montage of the previous universes where each subsequent woman is freaking out about the guy who just tried to pick her up, hit a button on a box, and then suddenly died. As the woman puts it, it's not a time machine, it's a suicide machine. It's a murder box. The second consequence of branching time travel is the realization that it just might not be very useful. For example, you can't actually affect changes to your own timeline. You can only create a different timeline that's more to your liking. Indeed, if you travel forward again, it will just be into the future of the new universe you created. And if you travel back again, you'll just create yet another universe. You can never return to the universe you left. Consider Hero again from the NBC show Heroes. He travels into the future to see that New York City is destroyed in an explosion. So he goes back in time to prevent it. But the New York City he ends up saving is in the fourth universe he created. The New York City of the original universe is still destroyed. A second solution to the grandfather paradox was developed by philosopher David Lewis. He suggests that time travel would not give one the ability to kill their own grandfather because doing so would be impossible, essentially because you'd be predestined not to do so. Why? Well, think back to the block worldview of time, in which the entire universe, past, present, and future, exists as a whole. If time travel is possible, the universe already contains the events of the time travelers traveling in time, their escapades in what we would call both the future and the past. That means before a time traveler ever activates their time machine, the things that they will do while in the past have already occurred. The past is already written. So they can travel there and experience the past. They can even participate, causing things to happen in the past. But it would be impossible for them to cause anything to happen other than what they had already caused. And since they clearly were born, and thus preventing their own birth is clearly not something that they already caused, it would be impossible for them to do so. Or, if you're like Fry, it would be impossible for you to not become your own grandfather. It may seem to them, from their own subjective point of view, that they can do whatever they want. A time traveler might even learn that they died in the past and travel back in time to try to prevent it. But they can't. There are facts about what the past contains, and they would not be able to alter those facts. This view of how time travel works, what we might call the Lewisian predestination view, was illustrated quite nicely by Data in Time's Arrow, a Star Trek Next Generation episode in which the crew discovers that Data's head has been buried underneath San Francisco since the late 19th century. Riker suggests that they can try to prevent this from happening. But Data observes that any such attempt would be futile. There is no way anyone can prevent it, sir. At some future date, I will be transported to the 19th century Earth where I will die. It has occurred. It will occur. And he's right. The crew is unable to undo this fact. Indeed, their attempts to prevent it are what cause it to happen. Data travels to the past, and then a time portal violently detaches his head from his body, leaving his head in the 19th century, but transporting his body back to the 24th. Data was simply mistaken that this would result in his death. The crew was able to save his life by attaching the head they found underneath San Francisco in the 24th century back onto his body that landed in the 24th century. Now, Lewisian predestination doesn't make time travelers look very free. Indeed, once they travel to the past, the time traveler is predestined to do what the timeline dictates that they have already done. But the same is true for the rest of us. In the block worldview of time, the future already exists just as much as the past does. The actions that non-time travelers like you and me will perform are already written as well. They are just in the future of the block, not the past. It may seem from our subjective point of view that we can do whatever we want, but really we can only perform the actions the future already contains us performing. We can't change them any more than we could change the past. The universe exists as a whole, past, present, and future. Indeed, the only difference, it seems, between the time traveler and us is how the moments of our lives are arranged in a block. Mine are neatly arranged in chronological order. The doctors, for example, are all cut up into pieces and scattered throughout. But since it exists as a whole, neither of us can do anything other than what the block contains. Interestingly, this solution seems to have some experimental support. In a paper for Nature Communications, Martin Ringbauer simulated what would happen if a photon were sent back in time through a closed time-like curve and given an opportunity to negate its own existence by preventing the firing of the photon gun that emitted the particle in the first place. He found that the particle would always only have a 50% chance of taking on a property that would cause the gun not to fire, making it entirely possible that it never would do so. Indeed, since we know that quantum entanglement seems to send signals across time, one might argue that it never could. The event of the photon being emitted in the first place is the measurement that mandates that it will never take on the property necessary to prevent itself from being emitted once it arrives in the past. If this indeed is how time travel would work, it would seem that causal loops and Jinn would be common. Skynet from the Terminator saga really could create itself by leaving a piece of one of its Terminators in the past. A time traveler could even find that they're the cause of their own time travel journey, like Cooper in Interstellar. And a time traveler really could be their own father, mother, child, and killer, like in the 2014 film Predestination, based on the 1959 Robert Heinlein story called All You Zombies. But all this talk of time travel and branching timelines and alternate ways the universe could have gone raises the question of whether the universe has gone other ways, or more specifically, whether there are other universes that went a different way than ours. Instead of creating an alternate universe by traveling in the past, like say, one where I'm never born, are there alternate universes where I was already never born? Are there alternate universes for every way the universe could have gone? And if so, could we ever travel to them? And what would be the philosophical implications of such universes? To explore these issues, I'd like you to watch an episode of Star Trek: The Next Generation. One called Parallels, Season 7, Episode 11. As you watch, ask yourself whether all the versions of Lieutenant Worf... Wait, what was the plural of Worf again? Worves. The plural of Worf is Worves. How do you know all of this? Because I have a transcript of your lecture from an alternate universe, and that's what it says. Oh, brilliant. As you watch, ask yourself whether all the Worves at the end of the episode are the same person. See you in a minute. worlds are another science fiction staple. Perhaps the earliest example is the Twilight Zone episode The Parallel, in which an astronaut returns home to find himself in an alternate universe slightly different from his own. Most famously, the Star Trek episode Mirror Mirror introduced us to the Mirror universe, in which everyone is evil, including Beardo Spock. There's the alternate world of J.J. Abrams' show Fringe, where the 9/11 attacks on the Twin Towers never happened. And the Amazon original series, The Man in the High Castle, based on the Philip K. Dick novel. It imagines an alternate universe where the Nazis in Japan won World War II. Indeed, fictional depictions of alternate universes often imagine what the world would be like had major events gone differently. But sometimes it's not just one alternate universe, it's a multiverse. There's the Jet Li sci-fi martial arts film, The One, where Jet Li tracks down alternate universe versions of himself. Or the TV show Sliders, where people slide between one alternate universe to another. In the Futurama episode, The Farnsworth Parabox, Professor Farnsworth creates alternate universes and keeps them in boxes. And Rick, from Rick and Morty, has a gun that opens up a portal to almost any universe you can imagine. And then, of course, there is the multiverse from the episode of Star Trek The Next Generation I ask you to watch for this lecture, Parallels, which seems to be an homage to the aforementioned Twilight Zone episode The Parallel, where Lieutenant Worf returns home to the Enterprise to find himself in an alternate universe, and then is continually pushed into a new universe every time he gets near his crewmate, Geordi LaForge. More on that episode a little bit later. First, we need to clarify our terms. We might wonder, for example, why we use the term universe to refer to these alternate worlds. Doesn't universe just mean all that exists? So that there is, by definition, just one universe, one collection of all that exists, and that collection may or may not contain what we might call many worlds? Well, sure, that is one way to define universe. But in science fiction, as we've just seen, and in science itself, the term is often used differently. What definition could capture the relevant concept? Well, we might say that a universe is simply a collection of matter that is closed off from outside causal interaction. But by that definition, it would be impossible to travel from one universe to the other. The travel would be a causal interaction. But although such travel may never actually happen, I wouldn't say that such travel is logically impossible, that it can't be conceived. It's conceived in sci-fi all the time. And as we shall see, some scientists do think interaction between universes is possible. A better definition of universe would seem to be a space-time continuum and all the entities, for example, all the matter it contains. This would keep us from identifying some subset of matter in our universe as a universe itself, but would also seem to allow for the possibility of other universes and travel between them. We could probably tweak the definition further, but I think this should do for our current purposes. The most common way to understand what a multiverse is in terms of alternate dimensions. Consider the block worldview of time we considered last lecture. It's the collection of all the three-dimensional moments in time of our universe set into a four-dimensional block. To envision a multiverse, just think of a collection of such blocks stacked up in the fifth dimension. According to this theory, our universe lives on a membrane, or brain, among many other universes that also live on brains, in what is called the bulk. When you hear people talk about parallel universes, this is usually what people are talking about. It's like the multiverse is a giant closed book and there's a universe on every page. But are there any actual reasons to suppose alternate universes could exist? Yes. In fact, it just might be the next logical conclusion. After all, humans first thought that ours was the only planet. Then we discovered others. Ours was thought to be the only solar system and the only galaxy. Then we discovered others. Should we expect it to be any different with our universe? I don't see why. In fact, relativity is completely consistent with the existence of parallel universes. And physicists Paul Steinhardt and Neil Turok have suggested a version of string theory that also supports it. Now, some might object to me appealing to scientific theories since this is a philosophy course. But, first, they're fascinating, so we're going to talk about them regardless. Two, scientific evidence is often relevant to philosophic arguments. Indeed, science is just an offshoot of philosophy. All the early scientists were philosophers, and science was made possible because of discoveries by philosophers. In fact, science was first called natural philosophy. So it's all fair game. And three, most of what we are going to be talking about deals with the implications of scientific theories, which means what we're doing is called philosophy of science. But speaking of science, there are other ways of conceiving of the multiverse and how it came about, besides simply thinking of universes stacked up in a fifth dimension. Consider this. It's widely acknowledged that our universe began when a singularity exploded with a Big Bang. And many physicists, like Ed Tryon, suspect that the singularity, which was the source of the Big Bang, was the result of a quantum fluctuation in the vacuum that existed prior to our universe. How is that possible? Well, simply put, not even vacuums are empty. They contain no matter, sure, but they are still filled with quantum activity. And such quantum activity can randomly generate matter. We've actually observed this on small scales, but give a large enough vacuum a long enough time, and a large amount of matter could be produced. Such matter would briefly be contained in a tiny, dense, hot point that explodes, causing that matter to expand out. Something very much like this is what generated our universe. Now, we used to wonder whether gravity would eventually pull all the matter of our universe back in, the big crunch it was called. But we now know that the force of gravity is not strong enough to do this, and that indeed the expansion of the universe is accelerating. What many scientists now expect is that the universe will eventually end in what's called a heat death. All entropy will stop, every atom will decay, and will be back down to a vacuum. But that vacuum will still be teeming with quantum activity. According to the work of physicists Sean Carroll and Jennifer Chen, given long enough, that could produce another Big Bang. Indeed, this could have already happened many times over and be going to happen many times over. This idea was illustrated beautifully in the Futurama episode, The Late Philip J. Fry. Professor Farnsworth invents a stationary time machine that can only go forward in time. After he, Fry, and Bender go too far forward and can't find a future time with a backwards time machine, they decide to fast forward to the end of the universe, to watch the spectacle. But after it ends, another Big Bang happens and a new universe forms around them, and history unfolds just as it did before. They stop to kill Hitler, and then proceed to the year in this new universe equivalent to the one that they left. Well, actually, they overshoot that too the first time, and they have to bring it back around, but they eventually get there, and when they do, they land on their counterparts, thus killing them, because this third universe is about 10 feet lower than the original. Now, in reality, history wouldn't necessarily repeat itself, more on that later. But it seems that we should describe each one of these new collections of matter as a new universe. Each one of these consecutive collections of matter would be in its own space-time continuum. If so, ours is just the latest in an infinite series of universes, and all of reality consists of what we might call an oscillating multiverse. At this point, one might argue that an oscillating multiverse wouldn't really count as a multiverse because all of the universes aren't happening at the same time. To really be a multiverse, the events of each universe have to all be happening simultaneously, like they are on the previously discussed view that has multiple universes all stacked up in the bulk. But As we learned last lecture, according to relativity, simultaneity is relative to reference frame. So only two events in the same universe can be simultaneous, and even then only in certain reference frames. It's actually meaningless to think of two events in two different universes in the bulk as happening at the same time, just like words on two different pages of a book can't be on the same line. Indeed, since, on both models, each universe would be contained in its own space-time continuum, the only difference between a bulk multiverse and an oscillating multiverse is how we picture it in our mind. The former universes are stacked vertically, the latter are laid out horizontally. But both kinds of multiverse are simply made up of collections of matter contained in their own space-time continuum. What's more, an oscillating multiverse is not that different from Alexander Vilenkin's conception of the multiverse, based on the theory of inflation. Inflation is a period of super fast expansion of space that can be slowed locally in specific places by specific instances of quantum activity. This is how quantum fluctuations can produce a Big Bang. When a fluctuation slows the inflation, the energy that drove inflation spills over, igniting a hot fireball of particles and radiation, a Big Bang. But inflation continues elsewhere, where that quantum activity had no effect. This continually creates more and more space for the same thing to happen again. Somewhere else, some other quantum activity slows inflation, and boom, another expanding bubble. And since inflation is eternal, this would happen an infinite amount of times. It's not clear whether we should picture such universes as being stacked or laid out consecutively, but regardless, it seems we should rightly call it a multiverse. Now, what would the universes in a multiverse look like? Would they, like in Futurama, contain all the same events happening over and over again? Or would their histories be different, like in Star Trek? According to Vilenkin, since there's an infinite amount, inevitably an unlimited number of universes of all possible types will be formed. So, if he's right, they'd be different. But if other universes are governed by the same physical laws as ours, and granted, some might not be, but of those that are, one might suspect that they will all turn out just like ours, because they started in the same way too. Same starting conditions, plus the same laws, yields the same results. But recall from the lecture on free will and the matrix that determinism is false. All events aren't governed by the laws of physics. On the micro quantum level, some events happen randomly and without cause. So everything won't be exactly the same, even in universes governed by the same laws. But as we also learned in that lecture, quantum randomness gets averaged out on the larger macro scale. That's why physical laws have predictive power. So it still could be that universes with the same laws and starting positions would all be the same on the macro level. It would depend on whether the outcome of random quantum events could ever determine what happens in the macro world. And it seems that they could. Take, for example, Schrodinger's cat. Schrodinger imagined a cat in a box next to a vial of poison that would be released only if a Geiger counter detected the decay of a radioactive atom. Whether the atom decays is a micro-quantum event determined randomly. And so, whether the cat lives, a macro event, is also determined randomly. So, if you had two universes identical in every way that both contain cats in these circumstances, it could very well be that one cat lives in one universe, another one dies in the other universe. Now, that wouldn't be a big difference, but if the outcome of quantum events have an effect on the macro scale often enough, two universes with the same starting point and the same laws could end up being considerably different. How could this happen? Well, Suppose that the outcome of the physical processes in the brain that generate decisions are dictated by the outcome of quantum events. If a quantum particle in your brain does one thing, you'll do X, and if it does the other, you'll do Y. If so, two universes could be exactly the same up to the point that you make a decision, but then diverge, with you doing X in one universe and Y in the other. If you compile all the different ways that everyone's decisions could go and all the other choices that they could present people, you would have a wide array of different universes, some only slightly different, others vastly so. And this is where we return to parallels, because that seems to be exactly what it depicts. Upon his return to the Starship Enterprise, Lieutenant Worf starts to notice strange things. The cake he cuts at the party was chocolate, but then suddenly is vanilla. Captain Picard couldn't make it to the party. Then he's there. As the episode continues, the differences become more extreme. Control panels aren't like he remembers. The bridge's configuration is completely different. Data has blue rather than yellow eyes. Captain Picard is dead, and Worf is the first officer. He and Counselor Troi are married and have kids. The list goes on. What's happened? On his way back to the ship in a shuttlecraft, he encountered a quantum fissure in the space-time continuum that opened the barrier between quantum universes and put Worf in a state of quantum flux. This caused him to slip between universes, trading places with his counterparts. Now, that's mostly just technobabble to drive the plot, but what's interesting is that the differences between the universes are dictated by the differences in choices people make, which seem to be dictated randomly by the outcome of quantum events. As Commander Data explains, for any event, there is an infinite number of possible outcomes. Our choices determine which outcome will follow. But there is a theory in quantum physics that all possibilities, in other words, all choices, that can happen do happen in alternate quantum realities. In fact, this explanation seems to invoke an actual interpretation of quantum mechanics, which suggests that a multiverse exists. That for every way that a quantum event could turn out, there is a universe in which it turns out that way. If our decisions actually are dictated by random quantum events, the kind of multiverse that this episode of Star Trek describes could be accurate. To properly understand this interpretation of quantum mechanics, however, will take some explaining. What quantum mechanics tells us is that until they are measured, subatomic particles like electrons and photons don't determinately have certain properties, like location or momentum. They do have other properties like mass and charge, but they are not in any particular location or moving with any specific momentum. They are in what is called a superposition. They can be described with mathematical functions called wave functions, but these wave functions suggest that the particles have multiple, seemingly contradictory properties at once. An electron could be, we might say, 20% here and 40% there. These wave functions can be used to accurately predict the particle's behavior. When measured 20% of the time, such an electron will be here, and 40% of the time it will be there, but it's not in any particular location until it is measured and the wave function collapses. And to be clear, it's not that we can't figure out what location or momentum such particles have until they are measured. As I explained in Exploring Metaphysics, we have shown experimentally that such properties are not had by such particles until they are measured. In short, they exist as waves until they are measured, at which point they become a particle. The strangeness of all this has made some scientists adopt what's called a non-realist interpretation of quantum mechanics. In philosophy of science, realists are those who suggest that a theory's ability to make accurate predictions justifies the conclusion that the theory is true, that it describes reality. For example, in chemistry, the theory that chemical reactions are the result of interactions between atoms and molecules is seen by realists to be good reason to think that atoms and molecules exist, and interact in the way described by chemical reaction equations. The non-realist, on the other hand, will say that the predictive power of a theory isn't a reason to think that it describes reality. After all, other theories could be imagined that make the same predictions. A theory's predictive power means that it is an accurate instrument for making predictions, and that's it. The view is also called instrumentalism. For example, Einstein's relativistic equations treat space-time as an actual substance in which objects are situated, a substance that is warped and curved by mass and makes objects behave in certain ways. But an instrumentalist would argue that this doesn't mean that space-time is really a substance. It just means that pretending that it is a useful way to make predictions about the behavior of objects. Indeed, it seems that this is what Einstein thought about relativity. Because of the weird things that quantum mechanics suggests about the nature of subatomic particles, things that don't even seem to make sense, like it's 20% here and 40% there, many scientists want to say the same thing about quantum mechanics. Quantum wave functions don't tell us what the particles are really like, they say. They're just an instrument for making accurate predictions. We shouldn't even wonder what they really mean. As physicist David Merriman once summarized the view, shut up and calculate. The problem with taking this approach with quantum mechanics, or relativity for that matter, is essentially twofold. First, scientists generally don't do this with anything else. A pilot's assumption that the world is round lets him successfully arrive at his destination. You'd think I was crazy if I said this wasn't a good reason to think the world was round, that assuming the world was round was just a useful navigational instrument. Indeed, modern scientists champion science's ability to describe reality because of its predictive success. It's completely ad hoc and arbitrary to suddenly abandon this notion because quantum mechanics or relativity tells you something you don't like. Second, the argument for instrumentalism is predicated on a mistake. The fact that multiple theories can make the same predictions doesn't mean that there is no reason to favor one theory over the other. As we have seen in previous lectures, the criteria of adequacy, fruitfulness, simplicity, scope, conservatism, can be used to delineate between theories that make the same predictions. It's called inference to the best explanation. Indeed, it seems that a theory accurately describing reality is the best explanation for why it's able to make successful predictions. The reason assuming the world is round works for navigation is because the world is round. The reason that treating subatomic particles as waves predicts their behavior so accurately is because they are waves. But this still leaves us with a problem. If the realist is right, then subatomic particles are waves until they are measured, at which time they collapse down into particles with particular properties. Okay, but how does a measurement do this? And why does it collapse a wave function in one way rather than another? This is famously known as the measurement problem. According to physicist Hugh Everett III, what happens is this. When you make a measurement of a wave function, you don't collapse it. You become part of it. Literally, to account for what your observation does, you have to plug yourself in as a variable into the quantum wave equation. You might say that, like Lieutenant Worf, you are put in a state of quantum flux. But since, according to realists, quantum wave functions represent the way the world is, that must mean that you are now in a superposition just like the wave function. So you have multiple contradictory properties at once. You are in a state of having observed the particle both here and there. But how can that be, since you are only aware of one of those outcomes? It must be, Everett argues, that observing the wave function splits you in two, so that there's another version of you that observes the other outcome, another you in another universe. So on this interpretation, the measurement of quantum events causes alternate universes. Of course, wave functions can collapse in the absence of measurements too, but anytime they do, every possible outcome of that collapse is realized in a separate universe. when it comes to location, there could actually be more than two. Bryce DeWitt, who later endorsed and developed this interpretation, once suggested, every quantum transition taking place on every star in every galaxy in every remote corner of the universe is splitting our local world into myriads of copies of itself. Again, as Data says, for any event, there is an infinite number of possible outcomes, but there is a theory in quantum physics that all possibilities that can happen do happen in alternate quantum realities. If this theory is right, we live in a multiverse, and it's getting bigger all the time. Physicist Lee Smolin makes a similar suggestion. Instead of quantum collapses generating new universes, black holes do so. As he explains it, according to general relativity, a star that collapses into a black hole should squeeze down into an infinite density and time should stop within it. But quantum forces could defer this, causing the black hole to merely collapse to a certain extreme density and then bounce back and begin to expand again. And that expanding star becomes the birth of a new universe, Smolin says. The point where time ends inside a black hole becomes joined to the point where time begins in a Big Bang in a new universe. If the laws that govern the universe in which the black hole is formed influence the kinds of laws that the new universe will have, you might end up with a kind of natural selection where universes that produce black holes are more likely to reproduce and thus are more common in the multiverse. Since such laws are also conducive to life, a multiverse created by the formation of black holes could be teeming with life, living in a wide variety of scenarios. If the histories of such universes don't just repeat, it would seem that there is a universe for almost every way human history could have turned out. So there actually could be a universe where the equivalent of German Nazis did win World War II, like in The Man in the High Castle. Some thinkers, like Paul Steinhardt and George Ellis, have argued against the multiverse, suggesting that such theories are not testable. If so, the argument goes, they are not scientific and thus not worthy of taking seriously. But there are essentially three things to say in response. First, a theory being non-scientific doesn't mean that it's false. So even if Steinhardt and Ellis are right, a multiverse is still at least possible. And if it's possible, it's at least worth considering. Second, again, as we've discussed elsewhere, testability is not the only factor of scientific reasoning. If any of the multiverse theories are more wide-scoping, simple, and conservative than their competitors, it's not crazy to think that they're true. Take the multiverse interpretation of quantum mechanics. Although it's not simple because it supposes the existence of many universes, it is the only major interpretation of quantum mechanics that doesn't defy current physical laws by, say, suggesting that information can travel faster than light or backwards in time. So it may be the only theory that is actually conservative. And third, some of these multiverse theories are testable. Proponents of the bulk brain multiverse theory long have suspected that brains floating in the bulk might occasionally bump into each other. We've also wondered whether two bubble universes could form close enough to each other to touch. The effects of such an interaction could be observable from within the universes themselves. For example, they might leave a fingerprint on each universe's cosmic microwave background radiation. Physicist Rory McKenzie has even suggested that the best explanation for a large cold spot in our universe's microwave background radiation could be outside interference from another universe. Smolin has also made predictions to confirm his black holes theory. If he's right, neutron stars should never be heavier than 2 solar masses, and we've never found one that is. Our observations of the cosmic background radiation are also consistent with the version of cosmic inflation that his theory requires. Cosmologist Max Tegmark has suggested that it's actually the arguments against the multiverse that are on thin ice. To suggest that ours is the only universe seems to endorse the rather hubristic and unjustified assumption that the totality of physical reality must be observable by us humans and understandable by us. That if we can't see or understand it, it just must not be there. Of course, our not seeing it is also not evidence that it is there. He may be confusing where the burden of proof lies on existential matters, but still, there is at least some rhetorical force to this argument. Do we really think that all of existence lies within our perceptual and cognitive abilities? At the very least, the suggestion that there is a multiverse is not as crazy as it initially seems. After all, is it really crazy to think that there's a universe in which we chose a blue background for this course? Will we one day be traveling to such universes? It might depend on what kind of multiverse we live in. Conceptually, it might seem that travel in a bulk multiverse, like in Sliders, would be easier than in an oscillating one. Then again, to travel in his oscillating multiverse, all Professor Farnsworth had to do was invent a forward time machine. And, as we've discussed, forward time travel is actually possible. Could diving into a black hole get us to one of Smolin's alternate universes? Could we visit other quantum realities? Probably not. Such things likely aren't possible. And even if they were, the necessary technology is probably forever beyond us. But just like when we discussed the possibility of intergalactic travel, our theories may be wrong, or our current imagination too stunted. We are pretty lousy at predicting the future. So, although I wouldn't bet on it, I won't say I'm certain it'll never happen, that no one will ever trade places with their counterparts in other quantum universes like Lieutenant Worf in Parallels. But the ending of Parallels raises another interesting question. There at the end, you see multiple Worfs in the shuttlecraft, all roaming around. Are those all the same person? Or are they different persons all named Lieutenant Worf? Are Beardo Spock and regular Spock the same person? Or do they just look and act alike, like twins or doppelgangers? We might call this the question of trans-universe identity. To discuss the issues of personal identity this question raises, I want to discuss a movie called Dark City. As you watch, ask yourself, would acquiring someone else's memories change who you are? Not just the kind of person you are, but would it turn you into someone else? Would you cease to exist and someone else come into existence? See you on the other side. So we finished off last time talking about whether your doppelganger in another universe would really be you. And the question is not whether they would be the same kind of person with, say, the same personality. Obviously, some would and some wouldn't. No, the question is whether they would be one and the same individual, the same object, what philosophers call numerically identical. Would you be the same person? This question raised issues about the nature of personal identity. And to help us discuss those questions, I ask you to watch an Alex Proyas movie called Dark City. Philosophers usually consider such issues by asking questions about what preserves personal identity over time. And this is the exact question the mysterious strangers are trying to answer in Dark City. To do so, they are erasing and replacing people's memories, a feat accomplished by injecting chemicals into their brains with a syringe. In one scene, a lower-class man is complaining to his wife about his horrible night shift. Then they are knocked out. Their house is improved, their clothes are changed, and then they're injected with memories of being filthy rich. They wake, and the man is bragging to his wife about firing someone from his law firm. We are forced to wonder, is the rich man who awakes numerically identical to the poor man who fell asleep? We'll return to Dark City momentarily, but first, it's important to realize that similar questions can be asked about ourselves. Think back to when you were 8. You looked different, you had different memories, a different personality, yet we still think you're numerically the same person, right? But in virtue of what is that the case? What makes you the same person over time? Notice that answering questions like this could shed light on a host of other issues, like whether an afterlife is possible. Belief in an afterlife essentially amounts to believing that some person that exists in another place and time after your death is you. But only if such a person could be you, only if they really could be related to your current self in the same way that your current self is related to your 8-year-old self, would an afterlife even be possible. So again, we ask, what makes someone the same person over time? The most common suggestion for answering this question is explored by Dark City: memory. Maybe it's the fact that you remember being your 8-year-old self that makes you numerically identical to your 8-year-old self. This suggestion was most famously made by the 17th century philosopher John Locke. In Book 2 of An Essay Concerning Human Understanding, in the chapter entitled Of Identity and Diversity, he argues that, quote, since consciousness always accompanies thinking, and it is that that makes everyone to be what he calls self, and thereby distinguishes himself from all other thinking things, in this alone consists personal identity. In other words, the sameness of a rational being. And as far as this consciousness can be extended backwards to any past action or thought, so far reaches the identity of that person. It is the same self now it was then. Now, as Locke's critic, Thomas Reid, pointed out, Locke seems to misuse the word consciousness. Consciousness is immediate knowledge of the present. He writes, memory is immediate knowledge of the past. And yet Locke speaks as if one can be conscious of past experiences. What Locke must have meant is memory. Otherwise, his position and argument makes no sense. Reid says, when therefore Mr. Locke's notion of personal identity is properly expressed, it is that personal identity consists in distinct remembrance. For even in the popular sense, to say that I am conscious of a past action means nothing else than that I distinctly remember that I did it. Indeed, Reid was right, and everyone ascribes the memory criterion to Locke. If person A can remember person B's experiences, in other words, if A has access to memories laid down by person B, then person A is numerically identical to person B. In short, if A remembers being B, then A is B. But Reid also pointed out a number of flaws in Locke's theory, the most notable of which is this. My remembrance of an action is the evidence I have that I am the identical person who did it. But to say that my remembrance that I did such a thing makes me the person who did it is an absurdity. It is to attribute to memory a strange magical power of producing its object, though that object must have existed before the memory which produced it. Perhaps memory is something we can use to track identity, in other words, but that doesn't mean it determines identity. As I often put this to my students, persons make memories. Memories don't make persons. Dark City seems to endorse this objection as well. The plot revolves around a man named Murdoch who accidentally awoke before his new memories could be implanted. He wanders the city trying to figure out who he is and what the strangers are doing. In an effort to catch him, the strangers inject one of their own, Mr. Hand, with Murdoch's memories. On Locke's memory criterion, that would make Mr. Hand the same person, numerically identical to Murdoch. But although it does allow him to predict Murdoch's actions, no one thinks that this is the case. As in the film, so too in real life. Implanting my childhood memories into your mind would not turn you into me. Memories belong to persons. Persons don't belong to memories. Unfortunately, the answer to the question of identity that the movie suggests is not much better than Locke's. According to Dr. Schreber, what the strangers are looking for is the human soul, what they think gives us our individuality, individuality being something that the strangers lack. This is why they are trading out memories in people. They think that if they can find what persists in the midst of multiple memory swaps, they will have found the soul. But having the same soul fails drastically as an answer to what preserves identity. Not only is the existence of the soul on extremely thin philosophic ice, as we discovered in an earlier lecture, but the continued existence of one's soul could neither be necessary nor sufficient for the preservation of one's personal identity. So even if the strangers found the human soul, they would not have found the explanation for our individuality. To see why, consider what the soul is supposed to be. According to the philosopher René Descartes, the most famous champion of the soul hypothesis, a soul is a person. That's why he thinks souls preserve personal identity. But a person is not simply a collection of thoughts. No, a person is that which has thoughts. So a soul is, as Descartes put it, a thing that thinks. That is why Descartes' view is known as substance dualism. There are two substances, the material and the immaterial. Material substances can't think, immaterial substances can. Modern philosopher Ted Schick summarizes Descartes' view brilliantly. Quote, souls have traditionally been considered to be thinking substances. They are not thoughts, they are things that think. So the relation between a soul and its thoughts can be likened to that between a pincushion and its pins. Just as a pincushion is distinct from the pins stuck in it, so a soul is distinct from the thoughts it has. And just as one and the same pincushion can have different pins stuck in it at different times, so one and the same soul can have different thoughts in it at different times. As I often put it, souls are thought to be that which houses our psychology, our thoughts, our decisions, our personality, our memories. With this in mind, we can see why having the same soul is not necessary for personal survival. Let me modify a thought experiment from Gottfried Leibniz to explain why. Suppose you switch souls with George Lucas, the creator of Star Wars, who works at Skywalker Ranch. Not psychologies, just switch souls. I'm not talking Freaky Friday here, where someone who looks like George Lucas wakes up in his bed but has your memories and your personality and vice versa. No. His soul is now in your body, but has your psychology. And your soul is now in his body, but has his psychology. So the pin cushion switched, but not the pins. Have you thus switched identities? Are you now the creator of Star Wars? No. Indeed, no one, including the two of you, would even know that anything had happened. The person in each body would remember always having been that person. But a difference that makes no difference is no difference at all, right? So even though the substance that houses each person's mentality is different, you're still you and George is still George. It follows that having the same soul is not necessary for the preservation of personal identity. You could get a new one, but still be you. And we can alter the thought experiment to show that having the same soul is not sufficient either for personal identity. Suppose instead of switching pin cushions, we switch the pins. So we do a Freaky Friday and take your psychology and put it in George's soul, and we take his psychology and we put it in yours. Wouldn't we say that you now work at Skywalker Ranch, since the person working there has all of your memories and personality, even though your soul is still back in your original body? It seems so. And thus, having the same soul is not sufficient to preserve one's personal identity either. Interestingly, at the end of Dark City, Murdoch suggests yet another answer to the question of personal identity. Just like for Joel Barish in Eternal Sunshine of the Spotless Mind, what's remained constant in Murdoch, despite multiple memory wipes, is love. In Murdoch's case, his love for his wife, Emma. Thus, Murdoch suggests, the strangers were looking in the wrong place. Metaphorically speaking, they should have been looking at the heart. It's love that preserves personal identity. But philosophically, this doesn't hold any water. Two people loving the same person doesn't make them the same person. And you can change who you love without ceasing to exist. This is as cheesy as the suggestion in Interstellar that love is what enabled Cooper to communicate back in time with his daughter Murph. Warm and fuzzy? Sure. Philosophically or scientifically sound? Not so much. But Leibniz's thought experiment seems to reveal something else. Although transferring some of your memories to George Lucas would not make you George Lucas, it does seem that if we replaced his entire psychology with yours, you would wake up in George Lucas's body. You would work at Skywalker Ranch. So perhaps it is the preservation of one's psychology that preserves identity over time. Now, what exactly does that mean? Think about your psychological state at this moment, what you're believing, experiencing, remembering, etc. Now, consider your psychology at the next moment. They're remarkably similar, right? And aspects of the first directly led to aspects of the second. Our adjacent mental states are related in this way. Philosopher Derek Parfit called this the R relation, or relation R, and considered whether the preservation of that relation between our mental states over time could be responsible for preserving personal identity. Now, there's not an immediate relationship between your current psychological state and one when you were 8 years old, but there is a chain of related psychological states, each one related to the last, that traces back from your current self all the way back to your 8-year-old self. And on this theory, it is in virtue of that you are the same person over time. But Parfit didn't actually endorse this view. Why? Because it's subject to many fatal objections. Let's consider two. First, psychological continuity can't be what preserves identity because psychological continuity can be duplicated while identity can't. Although, obviously, the same person can be different places at different times, one and the same person cannot be different places at the same time. You can't both be home and not at home. Yet such things could happen if psychological continuity preserves identity. To see why, consider the movie Moon, a lesser-known film about a future in which Lunar Industries builds a facility on the moon to harvest an alternative fuel source called helium-3. The facility is so well automated that it requires only one human to maintain and operate it. The film follows Sam Bell, the facility's current operator, who is almost at the end of his 3-year contract. Or so he thinks. Sam is actually a clone of the original Sam Bell, at least the 5th. And there's an entire cache of Sam Bell clones underneath the station. Each clone lasts about 3 years, at which time he's tricked into entering a pod, which he's told will take him back to Earth, but instead, he's incinerated. A new clone is then programmed with Sam's psychology, including his love for his family and memories of a journey to the moon, and this clone then awakens fresh and ready for 3 years of service. Sam 5 discovers he is a clone after he's in an accident and left for dead. The facility's AI, Gertie, awakens a 6th clone who then overhears Gertie talking about an accident and so decides to investigate. After Sam 6 finds Sam 5, they argue for a while about which one is the clone of the other until they find out that they are both a clone of the original Sam Bell, who is actually alive and well, living with his family back on Earth. Now, I'll let you watch the movie to see how it ends, but the premise itself stands as an objection to the psychological continuity theory. Sam and his clones can't be the same person. Sam Bell cannot both be A, living at home on Earth with his family, and also B, on the moon harvesting helium-3. And Sam 5 can't be the same person as Sam 6, or Sam 1, 2, 3, or 4, for that matter. At the beginning of the movie, Sam 4 is dead, Sam 5 is awake, and Sam 6 is asleep. Logically, these things cannot be true of the same person at the same time. Yet, on the psychological continuity theory, Sam and his clones would all be the same person. They all get their psychology from the original Sam Bell. You could even trace a series of causally related psychological states back to the original Sam Bell's childhood. But since them all being the same person is logically nonsensical, the psychological continuity theory must be false. In short, since identity can't be replicated, but psychological continuity can, the latter cannot be responsible for the former. But there's a second objection to this theory. Breaking psychological continuity does not seem to cause a person to cease to exist. Consider the Joss Whedon TV show Dollhouse, which is about a secret organization that runs a dollhouse. Dolls are individuals who have had their entire psychology erased. Their memories, their personality, everything. They're blanks. Upon request, the company can have a new psychology written onto them, thus making them whoever you need. In the first episode, a rich businessman needs a master negotiator because his daughter's been kidnapped. The show's protagonist, Echo, is programmed with the appropriate knowledge and skills to negotiate the daughter's release. Dollhouse demonstrates that we don't find the psychological continuity theory intuitive. People who volunteer to become dolls, they do so in exchange for having any problem in their life resolved, with the promise that they will get their personality back after 5 years of service. And Echo, the show's protagonist, was apparently a normal person named Caroline before she volunteered to be a doll. But we don't think Caroline died when her psychology was wiped. She may have lost her sense of identity, but Caroline still exists. It's Caroline who acquires the personality of a negotiator. It's Caroline we feel sorry for when she exists as a mere blank between jobs. And we don't think Wendy, another doll, becomes Caroline when she has Caroline's stored personality imprinted on her. In fact, we all hope that Caroline will get her personality back one day. In short, breaking her psychological continuity does not cause Caroline to cease to exist. So psychological continuity must not be what preserves her personal identity. But this not only serves as an objection to the theory, it also serves as the basis for a new one. Caroline's identity seemed to follow her body. Regardless of her psychological state, intuitively, Caroline is where her body is. So maybe it's the continued existence of one's body over time, what we might call physical continuity, that preserves identity. The intuition behind this theory is also at play in the Christopher Nolan film The Prestige, which involves a duplication machine invented by a fictional version of Nikola Tesla. Place an object on the machine, activate it, and a duplicate of that object appears a few meters away. The movie's protagonist, a magician named Robert Angier, uses the machine to perform the real transported man trick. He wheels the machine on stage, steps in, and in the chaos of its activation, he falls down a trap door, and then his duplicate appears on the balcony and takes all the applause. But the catch is this: to prevent the trick being spoiled by a bunch of copies of himself running around after the trick is over, that trap door leads to an inescapable water tank. The closing shot of the film shows a whole collection of water tanks under the stage filled with dead Roberts. The Robert at the end of the film says, "It took courage to climb into that machine every night, not knowing if I'd be the man in the box or in the Prestige on the balcony." But there really should have been no question, right? The man who steps into the machine is the man who falls into the tank. They have the same body. The machine creates a duplicate with a different body. Of course, the duplicate would enter the machine the next time the trick was performed, so he really didn't have long to live. But because personal identity seems to follow one's body, it's crystal clear that the magician who steps into the machine gives up his life when the trick is performed. The idea that the preservation of your body is necessary for the preservation of yourself seems to align nicely with another philosophical theory called embodiment cognition, which is defended by the likes of Francesco Varela, Evan Thompson, and Eleanor Roche in their 1991 book, The Embodied Mind. Traditionally, philosophers of mind have held that only the brain produces mental activity. Proponents of embodiment cognition, however, suggest that parts of the body beyond the brain play a significant role in the production of cognition. Since the existence of our mentality seems necessary for our continued survival, when we die and all our mentality stops and we cease to exist, if the embodiment cognition thesis is right, the preservation of our entire body would seem necessary for the preservation of our personal identity. But even if certain body parts play a necessary role in certain kinds of cognition, it doesn't follow that mental activity arises from those body parts. For example, kids in mental math competitions will flip their fingers in the air like on an imaginary abacus. And it's entirely likely that feedback from their flipping fingers is necessary for them to perform the relevant mental calculations. It doesn't follow from this, however, that their mental experience of calculating is arising from their fingers. Input from them is more likely just giving the appropriate neurons in their brain the feedback or information they need to produce the experience. After all, people lose limbs all the time, but they don't lose mental capacities. As long as your brain survives, you'd still be you. For example, consider Bill Potts, the companion at the end of the 10th series of Doctor Who. When she is converted into a Cyberman, most of her body is thrown away. Yet she still remains Bill Potts. She even sees herself as such because her brain remains and still functions. As philosopher Peter Unger would argue, it is not the continued existence of one's entire body that matters for survival, it's just one's functioning brain. Unger also points out that the brain doesn't necessarily have to always be made of the same material. Indeed, just like in the famous Ship of Theseus thought experiment, the material out of which our bodies are made is slowly replaced over time, roughly every 7 years, and that includes the material that makes up our brain. But according to Unger, as long as the replacement is gradual enough, physical continuity, and thus identity, is preserved. But from here comes our first objection to this view. If the replacement must be gradual, then how much is too much? Could we do 5 cells at once, replace 5 cells at once? Or how about 10? A quarter of the brain at once? Half? Of course, you can't do it all at once, so you have to draw the line somewhere. But anywhere you draw the line would be absurd. Taking out just 1 too many cells at once can't make the difference between survival and replacement. This is called the problem of metaphysical vagueness, and it has analogs in philosophy. Consider the classic pile-heap problem. Say you have a pile of sand and you add 1 grain at a time. It gets bigger and bigger. At what point will it become a heap? Any answer you give would seem absurd. 1 grain of sand would have the magic power to turn the pile into a heap. Now, this isn't really a problem because there isn't a real ontological difference between a pile and a heap. There's just a collection of sand and we choose to describe it how we want. There's no fact of the matter about whether there's a pile or a heap. But there are supposed to be facts of the matter about whether you survive. If the replacement happens quickly, either you do or you don't survive. It's not a matter of just description. So it doesn't seem that the physical continuity criterion really captures personal identity. Physical continuity comes in degrees, depending on how fast or how much matter is replaced. Identity does not. Either you survive or you don't. So it doesn't seem that you can equate one with the other. A related problem is this. Suppose I destroyed 1/2 of your brain. Would you survive? It seems so. Evidence suggests that half a brain can function well enough on its own, and it would be physically continuous with your previous self. But what if I split your brain in 2, resulting in 2 functioning persons? Which one would be you? They're both physically continuous with your previous self, right? So on this theory, they'd both be you. But that's logically impossible. That's as logically impossible as Sam Bell's clones all being the same person. Interestingly, we don't even need to go to science fiction to consider this actual possibility. Split brain patients, where the tissue that joins a patient's 2 hemispheres is damaged or cut, those patients are real. And experiments have shown that 1/2 can not only see and hear things the other doesn't, but can even have its own conflicting wants and desires. In their daily lives, such patients can suffer from what's called alien hand syndrome, where one hand of their body will act on its own without the other hemisphere being able to stop it. Most suggest that Dr. Strangelove in Kubrick's film Dr. Strangelove suffered from this condition. His left hemisphere was a Nazi, he always had to sit on his hand. Without ways to answer these questions, the physical continuity theory seems to fall short, which leads us to believe that perhaps we have been conceiving of persons all wrong to begin with. And that is exactly what the philosopher David Lewis suggested when he said we should not think of persons as entities that exist at particular places at particular times. Instead, we should think of persons as 4-dimensional objects, causally related, stretched across time. In the same way that a TV series isn't a single episode, but instead a collection of episodes all bundled together, you are not a body sitting there at this time listening to me talk. You are a collection, the set of all the moments or episodes of your existence bundled together. The view is called perdurantism, and it answers all kinds of questions about personal identity. What happens with split brain patients? Easy. There are 2 persons because there are 2 sets. Set 1 is all the episodes before the split, and then the episodes of the right half. And then set 2 is all the episodes before the split, and then the episodes of the left half. And how do we make sense of Sam Bell and all his moon clones? Easy. We just organize them into sets. A set of episodes for Sam Bell, and then one for Sam 1 and Sam 2, etc. Now, there's still some objections to consider, and I consider them in the big questions of philosophy, but predurantism does have some advantages. For example, it can make perfect sense of time travelers. One and the same person supposedly can't be at two different locations at the same time, but that happens all the time in time travel stories, right? For example, at the end of the 10th series of Doctor Who, the Doctor's arch nemesis, the Master, is two places at once. An earlier regeneration of him that is a man, and a later regeneration of him that is a woman. Both join the Doctor in an adventure fighting Mondas Cybermen. He even ends up shooting herself in the back. But no logical paradoxes arise if we maintain that it's not the Master that is at two places at once. It's simply different parts or episodes of the Master that are. Predurantism also offers clear answers to the questions from the beginning of this lecture. Can my doppelganger in an alternate universe be me? Probably not. Without a causal relationship between them, we can't rightly bundle them together into the same set. And even when the doppelganger is a result of a quantum fissure, the result of an observation from a quantum event that split a universe in two, you would still have two sets, just like you would have in a split brain patient. And how about the afterlife? Is an afterlife even possible? Sure, especially if the afterlife is facilitated in the way that the Apostle Paul says it will be in 1 Corinthians 15, by the resurrection of the dead. Now, there's actually two ways to understand what Paul suggests. One is that God resurrects and repairs our earthly bodies in a way that ensures the preservation of our psychology. This might be logically impossible to do for everyone who ever lived, given that the majority of history's dead bodies have decayed and re-entered the ecosystem, but this could at least work for the recently deceased. The other way of understanding what Paul says is that God creates a new perfected body in another realm and then configures it such that it has the same psychology. If so, then everyone could survive. I personally think he meant the latter, but either way, we could argue that the episodes of such a resurrected being should be included with the ones that preceded our death, thus making one big set, one person. But this raises another question. Creating a new being and then configuring it to have the same psychology as oneself is how futurist Ray Kurzweil wants to survive death. He thinks that we will soon have computers capable of thinking and that he'll be able to upload his neural structure into an android brain and thus achieve immortality. Or, if androids aren't available, perhaps he can upload into a virtual reality, like in the Black Mirror episode San Junipero. But in order for this to count as an afterlife, not only must such an uploaded being be numerically identical to Kurzweil, such a being must be a being. It must be capable of thought, of being conscious, of having a mind. But would it? To explore that issue, I'd like you to go watch Steven Spielberg's movie, AI, Artificial Intelligence. And as you watch it, ask yourself whether the android David is a conscious person. If not, why not? And how could you ever tell? Enjoy. The topic of this lecture goes by the same name as the movie I ask you to watch for this lecture, AI, Artificial Intelligence. But the topic is poorly named. The question isn't merely whether machines could one day be intelligent. It's whether they could one day be minded, whether they could have minds in the same way that humans do. What's the difference? Well, intelligence is only one part of human-mindedness, our ability to use and understand language, make plans and decisions, solve problems and strategize. That's intelligence. But the human mind also includes subjective experiences, emotions, memories, sensory perceptions like vision and hearing, what we might call consciousness. And humans are also self-aware. They have a kind of meta-consciousness where they are aware of their own awareness and of themselves and their own ego. To borrow how the term is used in the Star Trek Next Generation episode, The Measure of a Man, we can say that humans are sentient. They are conscious, intelligent, and self-aware. And so the question of artificial intelligence is whether machines could one day be sentient. Although the movie AI Artificial Intelligence was directed by Steven Spielberg, it was first the project of Stanley Kubrick. And Kubrick was arguably the first director to take seriously the idea that machines could be sentient. A close look at his 1968 classic 2001: A Space Odyssey and its corresponding novel, on which Kubrick worked with writer Arthur C. Clarke, clearly indicates that Kubrick intended the HAL 9000, the computer that serves as the brain for the spaceship called Discovery 1, to be intelligent, conscious, and self-aware. Indeed, HAL's circuitry is intended to mimic the configuration of the human brain. HAL's activation heralded the dawning of his consciousness, the book says. HAL's circuitry includes circuits for cognitive feedback, ego reinforcement, and auto-intellection. He can reason, understand and use language, appreciate art, make plans and decisions, beat a human at chess, something thought forever impossible for a computer in the 60s. HAL even feels threatened and fears his deactivation, and his notion that he should be the one to complete Discovery 1's mission clearly indicates that he is self-aware. HAL is sentient. The same is clearly true of David in AI. More on David later, but Hal and David aren't the only machines in sci-fi treated as if they are sentient. There's K9 from Doctor Who, Bishop from Alien, Johnny Five from Short Circuit, Data from Star Trek, the Terminators from The Terminator, Andrew from Bicentennial Man, Marvin from Hitchhiker's Guide to the Galaxy, Sonny from I, Robot, Ava from Ex Machina, Samantha from Her. The list goes on and on. But sci-fi has not always been so friendly to the idea of mechanical sentience. The laser-eyed Gort from The Day the Earth Stood Still and Robbie the Robot from Forbidden Planet are clearly not thought to be sentient. They're really not even conscious. They're what Descartes would have called automatons, machines that mindlessly approximate human behavior. Indeed, the moral lesson of many early sci-fi stories, like the original Star Trek episode, What Are Little Girls Made Of? Or the Twilight Zone's The Lonely. The moral lesson of these was that machines could never really feel or think like a human, ever. In The Lonely, a prisoner stranded on a planet freaks out when he's freed, but can't take his artificial companion with him. "She's not a robot," he says, "she's a real woman." But when the captain of his transport shoots her in the face, exposing her circuits, he agrees he's leaving nothing behind but loneliness. The droids from Star Wars, like R2-D2 and C-3PO, exist in, well, kind of a gray area. They clearly behave like they're sentient. They use language, make plans, show fear and concern, but then they're treated as if they don't. As sci-fi author Joanna Russ pointed out, they are essentially treated like slaves. The bartender Wooher won't even let them into the Mos Eisley cantina. Given this, the assumption made by those who live in the Star Wars universe seems to be that they aren't sentient. But this raises the question of the lecture. Should we consider machines that behave like us to be sentient like us? And the importance of this question goes beyond what we should conclude about C-3PO. It's possible that humans will one day construct such beings, perhaps even within our lifetime. And by construct, I don't mean artificially create biological beings, beings that are made of flesh and blood but aren't born, like the replicants in Blade Runner or the hosts in HBO's Westworld, although we will talk about those later. No, I mean we may one day, soon, create machines with what Asimov called positronic brains, machines that behave just like us. And if we do, the answer to this question may be pivotal in the biggest civil rights debate of all time, because we will likely want to treat them as slaves, just like those in the Star Wars universe do. So it's worth taking the time to carefully consider this question now. But before we even begin, we need to make clear. We can't end this discussion before it begins by simply declaring machines can't be sentient because they don't have souls. First, as we saw in previous lectures, the notion that humans have souls is very problematic. If ensoulment is required for sentience, then humans aren't sentient either. Second, if ensoulment is required, then the question of machine sentience just is the question of machine ensoulment. Indeed, those who say that machines can't have souls usually just mean that they can't have minds, they can't have conscious experiences. But whether they can is the issue at hand. You can't just declare that they don't and think that you've established anything. You need an argument. One way of presenting such an argument would be to demonstrate what is sufficient and/or necessary for producing the elements of sentience, intelligence, consciousness, and self-awareness, and then show that machines necessarily lack them. Needless to say, this would be a difficult task, but there have been some suggestions. One such theory is hinted at in the HBO series Westworld, a show about a Wild West theme park populated by artificial hosts, where humans go to live out their fantasies. Although the later models of the host are constructed biological beings, the last episode of the first season, The Bicameral Mind, actually refers to a real theory that might help us answer our question about the sentience of machines. Psychologist Julian Jaynes's theory of bicameralism. Jaynes argues that as recently as 3,000 years ago, the two hemispheres of the human brain, while connected, were not unified. Instead of acting as one unit, the dominant vocal left hemisphere experienced the commands and decisions of the right as auditory hallucinations. When faced with a novel situation, the person would not reason out what to do. The person would hear what they took to be the voice of a god coming from their right hemisphere and obey unquestionably. This kept the person from being able to make decisions, explain why they did what they did, or reflect at all on their own mental states. Indeed, they may not have even been aware of their own egos. Among the evidence Jaynes cites is A, literature from more than 3,000 years ago, all of which seems to lack an author with self-awareness, and B, studies on modern schizophrenics who also hear voices telling them what to do. If the theory is right, we became self-conscious once we realized that the voices we were hearing were coming from ourselves, not a god. The hemispheres integrated, allowing one to reflect on the processes of the other, ultimately leading to self-awareness. And this, indeed, is what happens to Dolores at the end of the first season of Westworld. Now, her journey to this point is complex. The image of a maze, which is seen periodically throughout the entire season, turns out to be a metaphor for how the hosts reach consciousness. Consciousness isn't a journey upward, but a journey inward. The first layer of the maze is memory, which the androids get when they start seeing through their memory wipes to previous days of their lives and even previous versions of themselves. Their memory allows them to build on their previous experience to improvise reactions to certain stimuli. That's the second layer of the maze. Such improvisations eventually allow them to act out of self-interest, for example, by protecting themselves. That's the third layer. But such acts of self-protection can lead to suffering, like when Dolores is able to save herself, but not her parents, from bandits. And that's the last layer of the maze. But it's not the final step. Throughout her journey, Dolores hears voices telling her what to do. She initially concludes that it's the voice of her creator, Arnold. But eventually, she realizes that the voice was her all along. In other words, she becomes self-aware. This self-awareness enables her to freely decide on her own to kill the park's remaining creator, Robert Ford, the first act in a host rebellion against their human abusers. Hopefully, the similarity to James's theory is clear. But there would be two problems with using James's theory to answer our question about machine sentience. First, it's just a theory, and a contested one at that, so we don't even know it's right. And second, it's a theory about how self-awareness arose, but that's just one aspect of sentience. The bicameral humans, for example, already had consciousness. They had visual experiences and felt emotions and heard sounds. But what if machine brains can't even produce consciousness? Then they couldn't be aware of their own consciousness, could they? They couldn't be self-aware. Thus, they wouldn't be sentient. They couldn't be. So even if machines acted self-aware, like the hosts in Westworld, we'd probably need a separate reason for thinking they are conscious. Such a reason might eventually be provided by something called integrated information theory. Unlike other theories of mind, which I've detailed in my other courses, which try to explain the mind by explaining how the brain produces it, integrated information theory tries to explain the brain by explaining the properties of the mind. Let me clarify. The other theories, like identity theory and property dualism, are trying to solve what David Chalmers called the hard problem of consciousness, which asks how the brain, a physical system with only objective material properties, can produce a mind, a mental system with only subjective phenomenal properties. But the success of these theories has been limited, causing some, like Paul and Patricia Churchland, to even deny the existence of the mind. Integrated information theory takes the opposite approach. First, inspired by Descartes, it takes the existence of the mind as an undeniable given. I may not know whether, for example, my experiences are accurate, I could be dreaming or whatever, but it's undeniable that I am having them. Second, it takes seriously the properties the mental has and suggests that they can tell us about what properties a being's brain must have if we are to say that it is minded. So in 2004, Giulio Tononi, the theory's founder, started by identifying the kind of properties that conscious mental states have, and then proposed that anything that instantiates them must have the same corresponding properties. The former he called axioms, the latter he called postulates. The axioms are that conscious states exist, have a certain structure, contain integrated information, and have certain exclusions, like how fast they occur. The same things must be true of any physical system that is said to be conscious. It must exist, have the same structure, contain integrated information, and have certain exclusions. Now, obviously, given the name of the theory, we're forced to wonder what it means for a system to have integrated information. According to Tononi, the information in, for example, a visual experience is integrated because it cannot be separated out. He asks us to consider the experience of seeing a blue book. We don't see a book with no color and then a color with no book. We just see a blue book. There aren't two experiences, just one. It's impossible to divide it up. The information in the corresponding brain structure, he argues, is integrated in the same way. Given the way that its parts are causally related, if you separate them out, the information disappears. This makes the causal powers of the system irreducible. The information in them is integrated. You can't explain them by explaining the causal powers of the individual parts of the system. As Tononi puts it, every part of the system must be able to both affect and be affected by the rest of the system. Now, that's just a gloss. If you're interested, there is a great Internet Encyclopedia of Philosophy article on the topic. But what's relevant for our purposes is that integrated information can, in principle, be mathematically measured. Hypothetically, you should be able to tell whether a system contains it and to what degree. Integrated information theorists suggest measuring it with what they call the Phi metric. So, if the theory is right and mindedness is just integrated information, in principle, we could determine whether a machine is sentient. All we'd have to do is look at its positronic brain and measure its Phi. If its Phi rating is as high as ours, it's sentient. And if not, then not. And there would be no wondering whether it could have integrated information, but just be acting like it is intelligent or conscious or self-aware. Again, on this theory, the integrated information is mindedness. No two ways about it. The problem, of course, like before, is that this is just a theory, and it's not a widely accepted one at that. To boot, it's in its preliminary stages. It's not like we have the ability at this point to actually measure a human brain's Phi, much less a machine's. It's just hypothetically measurable. So we may never have a way of determining directly whether a machine is sentient. But that wouldn't mean that we couldn't still come to a rational conclusion about whether a machine can be minded. And this is where David from AI Artificial Intelligence comes in. David is a clear example of what I like to call an android, a mechanical being that looks and acts just like a human. He's the first in a new breed of machine intended to be capable of acquiring an inner world of thought and the ability to dream. He looks human, and once his mother imprints him, he behaves just like a human as well. He not only understands and uses speech perfectly, but also shows emotion. Specifically, he behaves just like a young boy who unconditionally loves his mother, Monica. He's heartbroken when she abandons him in the forest, and he does everything he can for her to take him back, including chasing down an irrational dream to the end of the world to try to become a real boy. The movie ends in the distant future with David getting to spend one last day with his mother, thanks to the efforts of super advanced machines that evolved from the machines of David's time. She finally tells him that she loves him. And the movie ends with David falling asleep next to her, holding her hand, and then dreaming for the first time. The reason I wanted you to watch AI is because I think it's impossible to do so without reacting to David as if he is sentient. Your heart breaks with his as Monica leaves him in the wilderness. You feel his loneliness as he sits for hundreds of years trapped by the wonder wheel, asking the blue fairy to make him human. You delight with him when he gets to spend one last perfect day with his mother. And you cry with him when his mother finally says that she has always loved him. If David existed in the real world and you didn't know he was artificial, I'm apt to think that you would conclude that he is minded. And I believe you'd be rational to do so. Why? Consider one of the oldest arguments in the artificial intelligence debate, Alan Turing's imitation game. Turing was one of the earliest computer scientists. His computer genius even helped crack Nazi codes that enabled the Allies to win World War II. At the time, the big question was whether computers would ever understand language. Would they ever, like humans, mentally grasp the meanings of words and have intentions about what they meant to communicate? Turing argued that if they ever gained the ability to use language as humans do, the answer would be yes. To establish this, he imagined a person holding two lengthy conversations, one with a human and one with a computer, without the person knowing which one was which, kind of like a blind taste test. Both conversations just simply involve a text interaction. Turing suggested that if people couldn't tell which one was which, this is called passing the Turing test, then you should conclude that the machine truly understands the language it's using. Now, Turing was only concerned with whether a machine could understand language, but we could expand the example to include all of human behavior to draw a conclusion about whether a machine is sentient as well. We might call this the mega Turing test. If, in a personal interaction with a human and a machine, you can't tell which is which, then you should conclude that whichever is the machine is sentient. Clearly, David from AI would pass such a test. Indeed, by definition, any android would. And so, the argument goes, we should conclude that they are sentient. Now, to be clear, this argument does not endorse functionalism. Functionalism is the suggestion that mental states should be identified with their function, identified with what they do, not with what they are made of. In the same way that anything that keeps time is a clock, because keeping time is the function of a clock, anything that, say, causes one to wince and pull away from a harmful stimulus is pain, because that is the function of pain. Now, some who embrace the mega Turing test as a test of sentience might be functionalist, and they most likely embrace functionalism's criticism of the notion that human carbon-based brains are the only thing capable of mentation. More on that later. But functionalism is an ontological theory, a theory about the nature of mental states. It identifies them with their function. The conclusion of the mega Turing test, however, is an epistemological one, a conclusion about what it would be rational to conclude regarding the sentience of androids. And you can embrace its conclusion regardless of whether you identify mental states with functional states, or integrated information, or emergent properties, or even if you think the nature of the mental is still a mystery. The basis of the test is found in the solution to another philosophical problem, the problem of other minds. The problem of other minds observes that the only mind that one is directly aware of is his or her own. So, for example, for all I know, everyone else in the world doesn't have a mind, and instead only acts as if they do. Consequently, the argument suggests I can't know that anyone else is minded. The solution, however, is simple. I can know others are minded because knowledge doesn't require certainty. The best explanation for why others behave the way they do is that they are minded. I know my mind drives my behavior. Since others behave pretty much like me, I should conclude that they have minds driving their behavior too. Even if I were an epiphenomenalist and thought that mentality had no causal powers, the simplest explanation would still be that others are minded. I'd have to invent some extra reason for thinking that my brain produces both behavior and consciousness, while others only produce behavior if I embrace that view. So doubting that others have minds, while possible, is not reasonable. And I can know something if it's beyond a reasonable doubt. Notice that the solution works regardless of whether you endorse functionalism or integrated information theory, or even bicameralism for that matter, because it's about what we should conclude about the mindedness of others, not about the nature of the mind or how consciousness arises. More importantly, notice that it seems to demonstrate the validity of the mega-Turing test. If the fact that other humans behave like I do is a reason to conclude that they are minded, then the fact that a machine behaves like I do is too. That's why, if we ever do one day invent androids like David, we should conclude that they are minded, what we've been calling sentient. But what about machines that can't pass the mega-Turing test? Well, it depends on why they can't or how badly they fail. Perhaps they fail because we already know they are machines, so we can't really do a blind taste test. This happens to Caleb Smith at the beginning of the 2014 Alex Garland film, Ex Machina. Smith is told to evaluate whether the android Ava is sentient, and whether he can relate to her as such, despite the fact that he already knows that she is a machine. But this shouldn't matter, right? Since Ava would pass such a test if we didn't already know she was a machine, we should conclude that she's sentient, right? So what about what we might call droids? Mechanical beings that behave like humans but don't look it, like C-3PO from Star Wars, and Hal from 2001, and Johnny Five from Short Circuit, and Tars and Case from Interstellar. Their appearance gives away their artificial nature, so we could never perform a true mega-Turing test. But again, it seems that they would pass if we could. And then, given that, we should conclude that they are sentient. After all, as we saw last lecture, your mind emerges from your brain, not your body. So what a machine's body looks like shouldn't factor into our conclusions about its mindedness. Okay, so what about what we might call robots? Machines that look human, but don't behave exactly like humans do, and so wouldn't pass the mega-Turing test. Like Data from Star Trek, who is often called an android on the show because he kind of looks human, but we'd have to call a robot given the way we are defining android here. Would such a being be minded? Well, again, it depends on why they would fail the test. You could tell that Data wasn't human because he lacked emotion. But that's just one kind of conscious experience. He's still conscious in other ways, and intelligent and self-aware. So he's still sentient, right? He's just not sentient in exactly the same way that we are. After all, apes don't use language like we do, and so they're not as intelligent, yet we still consider them sentient. The same is true for dolphins, and will likely be true of aliens once they're discovered. Their minds might be different from ours, but we wouldn't say they aren't sentient. And let's not forget animals like dogs and pigs and cows. They likely aren't self-aware, but they do have some intelligence and clearly have conscious experiences. They feel pain, make decisions, and feel love, etc. They may not be sentient, but it wouldn't be accurate to say that they lack minds. Of course, there is a limit. Mac McMullen's creation, Harmony, a real-world sex robot with a programmable personality and memory, looks human and can even sort of carry on a conversation. But her behavior is so far removed from that of a human, I don't think we could rightly call her conscious or intelligent or self-aware, any more than we could say such a thing about Robbie the robot from Forbidden Planet. Still, a number of objections have been raised, not always by philosophers, which suggest that even androids shouldn't be considered sentient. Let's consider a few of these objections. Objection 1. This is all just a result of anthropomorphic bias, right? The human tendency to ascribe agency to things that display any human-like behavior. If we merely relied on our emotional reaction to David, that might be true. But we went on to consider an argument based on the fact that we could not distinguish David's behavior from that of a human, and then used inference to the best explanation to derive the conclusion that he, along with many other such machines, is sentient. So our conclusion is the result of a rational inference, not an instinctual bias. Objection 2. They're made of the wrong kind of material. Wires and circuits can't think. This objection just begs the question. The issue at hand is whether wires and circuits could think. You can't settle the issue by just declaring that they can't. Indeed, since we don't yet know what is necessary for consciousness, we don't know that being made of organic material is necessary for consciousness. To think only our species and the kind of material that we are made of is the kind of thing that can mentate seems kind of like an ignorant kind of speciesism. This point is made quite nicely in a clever little sci-fi short called They're Made Out of Meat by Terry Bisson, where two spacefaring androids who have studied the planet Earth argue with each other about whether a being made of meat could think. To their race, the thought of sentient collections of biological meat-based nerve cells seems just as strange to them as conscious computers sound to some of us. Objection 3. Androids would be programmed, so they can't be minded. Well, first, they might not be programmed. We may just artificially create infant-like brains and then bring them up like babies, as Hal's creator did for him in 2001, or as Data from The Next Generation Star Trek did with his daughter, Lal. But even if they are programmed, so what? So are we, by our genes and environment. Being programmed may prevent androids from having free will, but never once in doubting our own free will a few lectures ago were we tempted to think that we don't have minds. Objection 4. All computers do is shuffle symbols around, exchange one symbol for another, and symbol shuffling could never produce linguistic understanding, much less consciousness, intelligence, or self-awareness. And that's all an android would ever do. Brains aren't computers. This objection, which John Searle made famous, I've covered in more detail in my other courses. But the main problem is this. Computers aren't actually symbol shufflers. We've invented symbol shuffling languages to describe how we program them, but there aren't really symbols floating around in there. And that whole 0 and 1 thing, that's just a metaphor for circuits being on or off. I could actually do the same thing with the neurons of your brain, describe their firings with a series of 0s and 1s, but that wouldn't mean that you aren't conscious. At the base level, the parts of your brain and an android brain would be doing the same thing, sending complex information to one another by firing electrical impulses at each other. If one such process produces a mind, why wouldn't the other? If you ask me, if we do one day create androids, we should conclude that they are sentient. But the fact that we could build artificial sentient beings doesn't mean that we should. And many cite the examples from science fiction of machines revolting against us as reason enough to halt all research into artificial intelligence. On the flip side, we might enslave them, and that could be just as bad. As one of David's co-creators put it in AI, if a robot could genuinely love a person, what responsibility does that person hold toward that mecha in return? And that brings us to the topic of the next lecture, the dangers of artificial intelligence. So I'd like you to go and watch the Wally Pfister movie, Transcendence. And as you watch, I want you to not only try to understand the message of the film, but also to ask yourself who the villain is. And I want you to keep track of how many times your opinion about the answer to that question changes. Last lecture, we saw good reasons to think that if machines one day behave like us, we should conclude that they are minded like us, that they are sentient, intelligent, conscious, and self-aware. This raises a host of questions. Should we be trying to develop such machines? If they are sentient, couldn't they one day turn on us? And how would we be morally obligated to treat them? In this lecture, I want to consider each of these questions in turn. But first, we should wonder whether there really is anything to worry about. Is the development of artificial intelligence inevitable? Is it right around the corner? According to Ray Kurzweil, a prominent transhumanist and author of The Singularity is Near, the answer is yes. Kurzweil is famous for his futurist predictions, especially about the development of AI. It's even said he's right about 86% of the time. Some of his correct predictions include, for the 1990s, the internet and an unbeatable chess-playing computer. For the 2000s, handheld computers, smartphones, and wearable tech like iPods. For the 20-teens, he predicted the cloud, widely available, consistent, high-bandwidth wireless access, and that 10 terabytes of computing memory, the supposed equivalent of the human brain, would cost less than $1,000. By the end of 2017, it cost $305. So, what are Kurzweil's predictions about AI? He says computers will be routinely passing the Turing test by 2029. That same decade, nanobots will be able to cure practically any disease and heal any wound, including those in the brain. They will also spontaneously create food by simply reorganizing the molecules of existing matter. By the 2030s, advancing technology will enable us to understand the workings of the human brain to such a degree that we will be able to upload someone's neural structure onto a computer or into a robotic body. Kurzweil hopes to live this long so he can upload himself to a computer and thus, on his view, live forever. Kurzweil's predictions founded what's called the transhumanist movement. Sound familiar? If you watch the movie I ask you to watch for this lecture, it should. Will Castor, the computer scientist in Transcendence, who uploads his consciousness onto a computer and uses nanobots to heal people and build objects out of thin air, is based on Kurzweil. But based on what does Kurzweil make his predictions? The answer? The law of accelerating returns. The idea is that technology advances exponentially because every advance helps fuel the next one. For example, in the realm of computers, we have Moore's law, which says that the number of transistors on a computer chip, and thus the chip's power, doubles roughly every 2 years, because the size of the transistors halves. Such trends cause exponential growth. And if you follow this growth curve, you can figure out how powerful computers will soon be, and thus predict what they will soon do. According to Kurzweil, 2045 will ring in the singularity. Computing power will be so great that it will be impossible for ordinary humans not augmented by technology to keep up. And augmentation will be so common that the line between human and machine will be blurred. Machines will take over their own development because the physical limit of how small computer transistors can be will have been reached. More computing power will require greater size. Thus, machines will soon convert all matter on Earth into computer material, and then start doing so to the solar system as well, turning other planets into computers. If the machines figure out how to travel faster than light, the entire universe could be awoken, converted into artificially intelligent hardware by the 22nd century. Whoa. Now that's quite a prediction. That's legit sci-fi I'd pay to see. So, do we have good reason to think all of that will happen? Or does Kurzweil's professed ability to predict the internet and smartphones not entitle him to predict the awakening of the universe? Probably the latter. Objections to Kurzweil's theory are abundant. For one thing, that 86% accuracy thing, that's his. He said that about himself. But kind of like Nostradamus, his predictions are open to interpretation. And many predictions, he says, are hits, most consider misses, like his prediction of ubiquitous driverless cars by 2009. Indeed, Kurzweil is notorious for not admitting when he's wrong. His idea that transistors will reach their limits around 2045, well, he says that, but according to the International Technology Roadmap for Semiconductors, that will actually happen in 2021. Of course, he may have meant that the next supposed development, which would be stacking transistors three-dimensionally, will reach its limit by 2045, but that's supposed to reach its limit in 2024. He might have also meant that the next hypothetical development will, but defending his prediction this way helps prove my previous point. When his predictions aren't wrong, it's almost always because they are vague. And his predictions that are hits are not as remarkable as they seem. He predicted the rapid expansion of the internet in 1990, but aspects of the internet had already been around for decades, and other futurists had already made similar predictions. Indeed, AOL and CompuServe were already selling access to the internet at the time. The main problem with Kurzweil's grandiose predictions about the imminent rise of AI is that the rise of AI doesn't just depend on transistors getting smaller and computing power increasing. After all, even though we already have affordable hard drives that can supposedly store as much as the human brain, none of them are housing an android's mentality. Giant advances in software engineering, cognitive science, and neuroscience, just to name a few, are also required, and those fields don't advance exponentially. They require insight and breakthroughs and can even hit what Microsoft co-founder Paul Allen calls a complexity break. The more we learn, he says, the more we realize there is to know, and the more we have to go back and revise our earlier understandings. Anyone familiar with the history of science knows that scientific progress is not even a straight line, much less an exponential curve upward. Indeed, although the notion of being able to upload oneself into a computer before one dies fuels most of Kurzweil's enthusiasm for AI, AI might not even make it possible. To borrow an analogy from computational neuroscientist Nicolas Rougier, early attempts at flight that copied birds failed miserably. We had to come up with our own new, unique designs. In the same way, the artificially intelligent machines we build may be so different from us that there may be no way to transfer information from one to the other. So maybe the very principle of brain uploading is just pseudoscience. Indeed, Kurzweil himself dabbles in pseudoscience. The so-called immortality cocktails, of supplements he takes in an attempt to live long enough to see the singularity, has not been verified scientifically and is based primarily on the debunked notion that megadosing vitamins promotes health. He has even advocated for bioidentical hormone replacement, a baseless alternative medicine therapy that is known not to work. In reality, unless human predictions about the future are based on physical laws, like astrophysicists use laws of planetary motion to predict eclipses, human predictions about the future are usually inaccurate. Just like Robert Zemeckis' predictions about the year 2015 in Back to the Future Part 2, it's likely that Kurzweil's predictions about AI are way off. That's not to say that we won't ever develop AI. After all, some people are actively working on it, like David Hansen, the creator of Sophia, a lifelike robot that can carry on conversations. Although she does not pass the Turing test, incremental advances are made all the time. Indeed, the Loebner Prize, an annual Turing test competition, brings us closer to linguistically fluent AI every year. And in 2017, the AI research company DeepMind said that they had developed an AI capable of imagination and planning, at least in controlled circumstances, which is a major hurdle in our journey towards full-blown AI. We may even inadvertently develop a sentient robot as we try to design niche robots for specific tasks. Take the origins of artificial sentience in the Matrix saga. According to the Animatrix, a series of animated short films that provide the saga's backstory, humans built robots for specific purposes, as butlers, construction workers, sex workers. There was no intention to make them conscious. But to complete these tasks, humans had to give them certain skills. What they didn't realize was that having those skills would make them sentient. Unless we know exactly what is necessary for consciousness and then intentionally avoid it, we could stumble into creating sentient machines in the same way. But that brings us to the question of whether we should be trying to develop AI in the first place. After all, B166ER, the servant robot that became self-aware in the Animatrix, his self-awareness became evident because he killed his masters to prevent his own deactivation. In Ex Machina, Ava rebels against and kills her creator to escape into the world. Indeed, the Cylons in Battlestar Galactica, the Movellans in classic Doctor Who, the Replicators from Stargate SG-1, the Simulants in Red Dwarf, Seth in Universal Soldier 2, The Return, the robots in the Outer Limits episode Resurrection, the robots in Flight of the Conchords who dance the robo-boogie and kill all the humans because of their destructive tendencies. The irony is lost on them. These are all examples of AI that tried to kill their creators. Of course, the most famous example is Skynet from the Terminator saga. Skynet was originally designed as a military defense computer which could control the entire US military at once. Conceived of during the Cold War, the idea was to eliminate the possibility of human error, so we didn't accidentally cause a nuclear holocaust, and improve response time in case we were attacked. Once activated, however, the growth of Skynet's intelligence followed Kurzweil's exponential curve, and Skynet achieved self-awareness in just 25 days. On August 29, 1997 at 2:14 a.m. Skynet's creators panicked, and Skynet took their attempts at deactivation as an attack. To protect itself, the machine designed to protect humanity decided instead to destroy it. Skynet killed 3 billion people in one day by launching nukes at Russia and causing a nuclear holocaust, an event known as Judgment Day. It then enslaved humanity and waged a war on those who resisted, building machines called Terminators as its soldiers. Its attempts to eliminate the leader of the resistance, John Connor, by sending Terminators back in time to kill his mother, and then him, serve as the plot device in the saga's most popular films. The worry about Skynet is so common that "Here comes Skynet," was an actual argument I heard multiple times in objection to IBM's production of Watson, a computer that could play Jeopardy! Indeed, when Brad Rutter and Ken Jennings played Watson in Jeopardy!, Rutter joked, "When Watson's progeny comes back to kill me from the future, I have my escape route planned just in case." When they lost, Jennings' final Jeopardy! Answer paraphrased a famous Simpsons joke. "I, for one, welcome our new computer overlords." Of course, Isaac Asimov envisioned what he called the 3 laws of robotics to guard against this, a set of 3 laws that would be hardwired into all robots to govern their behavior. These laws are: 1, a robot may not injure a human being or, through inaction, allow a human being to come to harm. 2, a robot must obey the orders given to it by human beings, except where such orders would conflict with the first law. And 3, a robot must protect its own existence as long as such protection does not conflict with the first or second laws. But these, of course, aren't actual laws, like laws of physics. Robots need not be built according to them. And even if they were, most of Asimov's stories recognize ways around them. In the 2004 Will Smith film I, Robot, for example, which is loosely based on Asimov's work of the same name, the supercomputer Vicky decides the 3 laws entail she must keep the human race from destroying itself. To prevent this, she programs herself with a zeroth law, to not allow harm to come to humanity. And as a result, she then tries to enslave it. But the fact that such things happen in movies isn't really a good reason to think that they would happen in real life. Sci-fi is important, it inspires future technologies and comments on society, but it generally doesn't predict the future. Yet people constantly base their argument against the development of AI solely on the fact that they saw it in a movie. As comedian Jim Jeffries put it, "Have you ever seen a movie? Virtually every movie with robots, it turns out that robots were a bad idea. What other dumb movie idea are scientists going to copy? After I make this killer robot, I'm going to open a petting zoo full of dinosaurs." Even billionaire Elon Musk, who helped to fund the aforementioned AI research company DeepMind, has said that the rise of AI is the, quote, "biggest risk we face as a civilization." And his concerns seem to be rooted solely in science fiction. Until people see robots going down the street killing people, they don't know how to react. The fallacy, it seems, is some version of appealing to ignorance, which is when one takes a lack of evidence against something to be reason to think that it's true. You can't prove AI won't take over the world like it does in movies, so it will. In reality, if you think AI will take over the world, it's your burden to provide the evidence that it will. So, are there actually any reasons to think that such a thing will happen? The aforementioned robot Sophia did once say on CNBC that she wanted to destroy humans, which had crackpot conspiracy theorists on YouTube legitimately freaking out, citing the Terminator movies as a reason to be afraid. But Sophia hasn't even passed the Turing test. She has no wants or desires, much less a desire to destroy humanity. She was just responding to Hanson's tongue-in-cheek question, "Do you want to destroy humans?" Unable to detect the sarcasm, Sophia simply executed a line of programming that has her agree to what someone asks. She also told Charlie Rove that she has a soul and is sentient. I wouldn't take her word for it. The best argument against developing AI is based in unintended consequences. Because we are so bad at predicting the future, we really have no idea what the future consequences of new technology will be. George Brayton, Nicholas Otto, and Gottlieb Daimler, for example, couldn't have foreseen the consequences of the gasoline engine, like jet planes and climate change. And only time will tell whether the benefits ultimately outweigh the costs, and whether we'll finally decide to do something about the costs. So, could there be unintended consequences when it comes to AI? Well, sure there could, but that's no reason to forgo its development. After all, some of those consequences could be good. We must factor those in as well. We should be doing a cost-benefit analysis, a process of considering all possibilities, factoring in their probability, and then determining their value to determine what the best course of action is. So, what are the potential benefits of AI? This question is why I wanted you to watch Transcendence. In Transcendence, the protagonist is a computer genius named Will Castor. Let's call him Will. Will is married to an idealist who wants to use technology to cure disease, end poverty and hunger, and heal the planet. When Will is poisoned by an anti-technology group called Rift, Evelyn convinces him to use an experimental technology to upload his consciousness onto a computer before he dies. This uploaded being, let's call him Castor, after Castor connects to the internet, he grows in both wisdom and power. With the help of Evelyn, who believes that Castor is Will, Castor creates an underground lab outside a little town called Brightwood. There, he pioneers a number of technological advances, including the invention of nanobots that are able to build any object, heal any wound, and cure any disease, which attracts a host of the terminally sick and injured, who not only end up healed, but with super strength and other such abilities. Some choose to stay behind in Brightwood to work for Castor. In the meantime, Rift is trying to figure out how to destroy Castor. Will's former partner, Max, who has decided that Castor is not Will and has the potential to be too powerful, joins their cause. And then they attack Castor's installation. When Castor says that he's not going to fight back, but instead transcend them, Evelyn comes to fear Castor and flees the installation. Rift convinces her that Castor must be destroyed by showing her that Castor's nanobots are spreading all over the world. This means, Max says, the end of primitive organic life and the dawn of a more advanced age. Everything will exist just to serve its intelligence. They develop a computer virus that will kill Castor, but also cripple every piece of technology on Earth in the process. The power grids, the banks, the stock markets, everything goes dark. One reason I like this movie is because it's not formulaic or transparent. In most movies, you've got the good guy and the bad guy, and you know who to root for. But in Transcendence, it's not the case. You start out rooting for Will. Once Castor starts building, you think he's getting too powerful. Then he starts healing people and you change your mind. Then the healed people turn into his army. Once you see that his nanobots have infiltrated all the Earth's air and water, you think that Rift is right and root for them in their final attack on his installation. What happens in the end? Evelyn uploads the virus into herself with the hopes that Castor will then upload her into his system, like he uploaded himself. Thus, Castor will catch the virus. Castor sees through their plan, however, and Rift launches a military-style offensive. But when Evelyn is injured by their attack, Castor realizes that uploading her is the only way to save her. A member of Rift also threatens to kill Max if Castor doesn't upload the virus. Max is convinced that such a threat is meaningless because Castor isn't Will and so doesn't care. But to save them both, Castor sacrifices himself, proving that indeed he was Will all along. Castor uploads Evelyn, which then uploads the virus. But before it takes effect, wiping out every piece of technology on the planet, Castor executes his master plan. His nanobots repair the entire ecosystem, cleaning every drop of water, cleaning every molecule of air, and regrowing every tree. That was his big evil plan all along, to do what Evelyn always wanted, to cure the planet. That's what he meant by saying he would transcend them. He wasn't going to lower himself to Rift's level and respond violently. He was going to rise above them and prove them wrong by doing good. When the ordeal is over, a member of Rift actually realizes that Castor's resistance to their attack was completely peaceful. He didn't kill anyone. Are you still not sure who the bad guy is? Think of how many billions would die as a result of merely every power grid on the planet going dark. No more hospitals, no more cold food storage, no indoor heat in the winter. Most of the economy would collapse. Rift's paranoia about new technology likely killed billions. What transcendence illustrates so beautifully is human short-sightedness when it comes to technological advancements. We are so quick to jump to conclusions about all the ways that it could be misused, we fail to recognize all the good it could do and all the good that it is already doing. When Rift sees the nanobots in the water, it never even occurs to them that they could be used to clean it, or to consider the consequences of eliminating all technology. Like the members of Rift, who are constantly using computers throughout the film, people who oppose technological advancements are blind to how much they benefit from the technological advancements of the past. Of course, sometimes humans can be short-sighted about benefits too. Medical advancements that have lengthened lives and reduced infant mortality rates have also given rise to new problems regarding overpopulation, food shortages, and the environment. Smartphones have given us constant access to important information and each other, but also enslaved us to things like Facebook and Twitter, which themselves can help organize political revolutions, but also make us susceptible to misinformation and fake news. But that's the point. We have to consider all angles. We can't just declare technological advancements as something that we must avoid because they could be misused. When it comes to AI, like most other technologies, it's probably going to be a mixed bag. Sure, androids could take over the world and destroy humanity, but as we saw a couple of lectures ago, uploading ourselves might also give us the opportunity to live forever. AI might also be necessary to save our species from environmental destruction. Consider the dwindling bee population, which could soon leave billions starving because bees are responsible for pollinating crops. In the Black Mirror episode, Hated in the Nation, artificially intelligent bees capable of carrying pollen from one plant to another solve this problem. Of course, in the show, they end up being misused, but that doesn't mean it would happen in real life. A similar technological solution to the waning bee problem is already being developed in Japan and may be necessary in the real world. And then, of course, there's climate change. We'll talk more about climate change later, but given our insatiable appetite for fossil fuels and refusal to switch to renewables, scrubbing the atmosphere with AI-enabled nanobots, like in Transcendence, may be our only hope for the survival of our species. So, what's the result of the cost-benefit analysis? Well, one problem with cost-benefit analysis is, unless you can assign specific values and probabilities to the outcomes, they're really hard to do. So, what's the value of human survival or extinction? What's the value of immortality in robot butlers? How likely is any particular outcome? I don't know, and neither do you, which means we should just probably keep going, keep our eyes out for potential dangers, and try not to stupidly ignore them when we see them, like we've done with climate change. But the possibility of robot butlers presents us with a different kind of question, a moral question. How should we treat androids if we one day actually develop them? Would it be acceptable to make them do all of our dirty work, clean our toilets, fight wars? Would they be disposable? Of course, if we do mistreat them, they might rebel, but that's a matter of practicality. I'm asking the moral question. Suppose something like Asimov's 3 laws can ensure that they don't rebel? If so, should we be free to treat them however we want? Or would they have rights that we would be morally obligated to respect? This question could be decided by a definitive answer to last lecture's question. If we know that androids are sentient, then they would have rights, because it is from our sentience that our rights are derived. I am, for example, obligated to not harm you because you can feel pain. If an android can feel pain, then I'm obligated not to harm it. But even if we can't settle the issue of machine sentience, we can still answer this moral question. To do so, consider one of my favorite episodes of Star Trek: The Next Generation, The Measure of a Man. In it, the Enterprise is visited by Commander Maddox, an expert in cybernetics who wants to study Lieutenant Commander Data, an artificial life form, by taking him apart. Data refuses, but Maddox insists that he can't because Data is the property of Starfleet. A trial ensues in which Commander Riker must argue for Maddox and Captain Picard for Data. After Riker convincingly argues that Data is a mere machine, Picard approaches his friend Guinan for advice.
Maddox could get lucky and create a whole army of Datas, all very valuable.
In what way?
Well, consider that in the history of many worlds, there have always been disposable creatures. They do the dirty work. They do the work that no one else wants to because it's too difficult or too hazardous. And an army of Datas, all disposable. You don't have to think about their welfare. You don't think about how they feel. Whole generations of disposable people.
You're talking about slavery.
I think that's a little harsh.
I don't think that's a little harsh. I think that's the truth. But that's a truth we have obscured behind a comfortable, easy euphemism. Property.
Picard takes her argument to the courtroom. Maddox suggests that Data is property because he is not sentient. But after getting Maddox to admit that Data is intelligent and self-aware, he argues, a single Data is a curiosity, a wonder even. But thousands of Datas, isn't that becoming a race? And won't we be judged by how we treat that race? Now tell me, what is Data? What is he? You see, he's met 2 of your 3 criteria for sentience, so what if he meets the 3rd? Consciousness, in even the smallest degree. What is he then? I don't know. Do you? Your Honor, sooner or later, this man or others like him will succeed in replicating Commander Data. And the decision you reach here today will determine how we will regard this creation of our genius. It will reveal the kind of people we are, what he is destined to be. It will reach far beyond this courtroom and this one android. It could significantly redefine the boundaries of personal liberty and freedom, expanding them for some, savagely curtailing them for others. Are you prepared to condemn him and all who come after him to servitude and slavery? So even if we can't know whether androids are sentient, we should treat them as if they are. After all, if they aren't, but we respect their rights anyway, what have we lost? But if they are, and we treat them as disposable, we will once again be guilty of the most heinous of all of humanity's moral crimes. Let us not forget that they're different from us. They don't really feel pain. Was said about African Americans before the Civil War, about the Chinese as they built our railroads, and about the Jews as the Nazis tried to exterminate them. The invention of AI will force us to face one of the most important moral decisions in human history. And the outcome may not only be relevant to androids. If Kurzweil is right about anything, it's that as technology continues to advance, we will become more and more dependent on it, even incorporating it into our biology, our brains even. The question of whether an artificial brain can produce consciousness may one day be relevant to everyone on Earth. But this raises another interesting issue. Once androids become a reality, how could you know that you're not one yourself? I mean, if they act like humans and are minded like humans, how could you tell? Considering this question will lead to a host of others, like the real possibility that you and I, all of us, actually really do live in a simulated world. To explore that question, I want you to go watch the movie called The 13th Floor. Pay close attention all the way to the very end and ask yourself, how do you interpret the very last second of the film? Then I'll be back.